Okay, let's go ahead and proceed. I was just taking a peek at who's turned in what, and on the superposition theorem, not everybody's turned that in. And I was wondering, were there probably some questions remaining on that that some of you might have. I was looking at the 555 multi-sim timer exercise. That one should have been done because I've given everybody a PowerPoint on how to acquire multi-sim for free use for 180 days. That's half a year. So you should have multi-sim loaded and working on that. And so just as a quick call, let's go ahead and move some things around here. Keep an eye on two screens. Here's, first of all, let me go ahead and take roll. So we have Rebecca's here. We have Gabe Orozco here. Andrew, is Kyle with you? Andrew, is Kyle with you?
Yeah, he's right here.
Okay. All right. So Kyle is there. Pauline is here. And then Christian is here. And we'll see Rolando shortly. All right. Now, with that, and hopefully we'll see Mr. Lau shortly also. With that being said, let's double check again where we stand. Those people who have submitted the multi-sim, I won't worry about. So Rebecca, were you able to get multi-sim installed? Microphone?
Not yet.
Okay, I can help you with that.
Yeah.
So multi-sim, that's all right. We'll work on that. That's not insurmountable. It's not hard to do. It's very fast download, and it doesn't cost you anything. And then the Lao guy, we don't know about. So it's really just, all right. So this one's a question mark. This one is not yet. All right. Now that being said, that's fine. Now let's take a look at, oh, here's Rolando. So let me grab the correct mouse and get Rolando in here. Okay, Rolando will be joining us. Nice. Welcome, Rolando. So what I was doing was, let me go ahead, put down Rolando. Rolando is having here, and I'll keep an eye on the screen as well to see how things are coming along. All right. We had a number of things that were assigned for us to look at for this week. One of the big point items was in week 11, from week 11 through week 12 last week, there were some catch-up things that I put in the email for y'all to get caught up on. And one of the most important things in week 11 would have been looking at all of the videos pertaining to capacitance. We talked about capacitance several weeks ago, and let me get to that on here for us. So not this. Let me get to here, and let me get to here, and let me get to here, and let me go to week 11, and I'll share my with you in a moment. Okay, so let's go ahead and share screen just so that you can see what things are looking like. The videos are short, so and you get to watch them over and over again, but it is important that we get to them. So here's my share screen for Canvas. Move this over to here, and then I'll move this up over to here and do this. Okay, all right, this will work. All right, so in week 11, the several things on capacitance online activities. So in week 11, under capacitance online activities, you'll see this on your screen. Everybody is seeing my Canvas screen? Yes, thumbs up? Okay, yes, okay, good. So on the Canvas screen, just like what we've set up before, there is a sign-off sheet for you to sign off the dates that you review the different tasks. So the sign-off sheet is an Excel sheet. I'll open it up. It'll drop down to here and open it up. And here's the Excel sheet. Corrupt cannot be opened, really. I can open up another version. That's not a problem. Something happened. Don't know. I don't care. Not a big deal. I will go to here and dates and move this up. Here we go. Okay, capacitance sign-off sheet will look like this. Okay, and it goes to list 5 videos that you need to watch. And the videos you can access by copying the URL here. So I copy, Control C, and then go back to my browser. Come on, screen. Mouse. Here we go. I will just do it this way. Curriculum. Okay, and then just add one here and paste. And they're really nice visual and sometimes auditory discussions. The electrostatic charge of a capacitor, because we talked about a capacitor. What does a capacitor do? The fundamental thing that capacitors do is that they store charge. And this goes to talk about how that happens. So we have, they call 2 plates separated by a special type of insulating material. If the insulator is used in the construction of a capacitor, it has a special name. It's called a dielectric. So we have different kinds of insulators. Rubber is an insulator, glass is an insulator, wood is an insulator, but those types of insulators are not used in the construction of a capacitor. So those are simply insulator materials. But some insulator materials, such as ceramics, electrolytics, plastics of some sort, tantalum, mylar, those special insulators can be used in the construction of capacitors. And so any insulator material used in the construction of a cap is called a what, according to my screen? Everybody say the word dielectric. Dielectric, okay? So that's the distinction here, and that's what you want to know. It's a special insulating material. And it goes to talk about, okay, what happens when we apply voltage to this, and we will be able to store charge. So here's the discussion about charging a capacitor. Here's a DC power source. Here's a capacitor, and we close the switch. Before we close the switch, there is no charge on the capacitor. The 5 volts on this side, we have nothing on this side. There is no current moving in the circuit because the switch is closed, yes? Now, when I go to do this, it says the charging, it says here, the charging action begins as the DC voltage is connected across the plates with the closure of the switch. So once I close this switch, the electrons will start to accumulate on the bottom surface of this capacitor, and the top surface of the capacitor will develop a deficiency of electrons. Any electrons that would have been there are immediately attracted to the positive side. So there will be a deficiency of electrons. What do you call a deficiency of electrons? What charge, what polarity is there if we take away the negatives? All that's left is positive. So this side of the cap, the upper side of the cap, will become positive. The lower side of the cap will accumulate electrons. It will become negative. So as we move this along, here I get to close the switch. So watch what happens in this when I close the switch. You see the electrons are moving, in this case in a counterclockwise fashion. The electrons are shown with the red dots. And what happens is the electrons will accumulate on the bottom plate, and whatever electrons were at the top have moved away from that to go to the positive. The capacitor will charge up to whatever voltage is applied. So if my voltage applied is 5 volts, this will charge up to 5. If this is 10 volts, it'll charge up to 10. Once this capacitor is charged, there is no more electricity flowing in the circuit. So I will show this again. See the electrons accumulating on the bottom, see the electrons leaving the top. And once this is charged up to whatever the voltage source is, the charging will stop, the current will stop. But there is a lot of current that happens until it reaches full charge. Did everybody see that action? That's really significant for you to notice because it leads us up to a discussion. That charging of the capacitor does not happen immediately. It takes some time for this capacitor to reach full charge. It takes what we call 5 time constants, and that's described in another video. So let's go to the next one. So it goes to say that the negative supply terminal forces electrons where? To the bottom plane, okay? And then the capacitor, and let's see what it says. Yeah, electrons are displaced, right? Okay, here we go. What happens then, the displacement is large when the capacitor is first charging, and it tapers off near full charge as shown by this curve. So it's not a straight line, it's called an exponential curve. And so the current starts off as maximum current. The moment we close that switch, bam, the current starts flowing and it flows immediately. It's really, really high current. And then as this starts to accumulate in negative charges on the bottom, and as this loses negative charges to become positive on the top, the amount of current gradually decreases until there's no more current. There's no more current when the capacitor is fully charged. There's no more electricity moving. Once that capacitor reaches full charge, current stops, okay? The danger to you and I as technicians is if we go to touch that capacitor after it reaches full charge, is we could be shocked. And we could be shocked very, very quickly with a pretty nasty shock. All right, so let's see what happens next. So when a capacitor is fully charged, says the voltage across the plates equals supply voltage. And the charging current says what? It stops. Okay, now moving right along. Capacitor charge, so you have the insulator material in between, it's called the dielectric, and it gives us the appearance that electricity is flowing through it when actually not. What happens is there's what we call an electrostatic field that's formed between them. And so the electrons will accumulate on the negative side of the cap, and electrons will disappear or be removed from the positive side of the cap. And they have lines of force, and this is really good information. You can read this again when you review this. Polarization of the dielectric, again, you can read this in greater detail. Your book also does a good job of explaining this, but the video is nice to be able to see how things are working. Most important, now that's the charging of the capacitor. Then we also have discharging of the capacitor. And the discharging of the capacitor is also controlled because it doesn't discharge immediately. It discharges over 5 time constants. And let's see how that works here. So in this particular illustration, what's being shown, and let me go ahead and change the view on this guy to here. Okay, this will give you a greater view. And it goes to show we happen to have the capacitor charged. So when I go to press the button, that means the switch will switch over to this side. Right now, the switch is on the left. As the switch is on the left, the negatives will accumulate on the bottom. All the electrons will disappear from the top, going to the positive plate of the source. There is a difference of charge on either side of the cap. The cap has voltage across it. The cap will be charged up to whatever voltage the source is. Now that it is charged, if I flip the switch over to the right-hand side, there will be a continuous path for the capacitor to release its charge. So the electrons will leave the bottom, flow through a switch here through the resistor so that the lamp will light up. And then this will continue working to release the current from the capacitor until all the charge has been drained. Until, what word did I say? All the charge has been drained. So let's watch and see how that happens. Discharge the cap. There the electrons are leaving, flowing through, light lights up, it's red, until all the charge is gone. Once the charge is gone, there's no more current flowing through. There's no more current flowing through. That lamp is now off. I'm going to show this again. We've recharged the capacitor. When I go to press the discharge button, the switch will switch over to the right, and all the electrons accumulated on the bottom will leave, flow through the resistor and lamp, light up the lamp, and then the electrons will flow through the lamp and accumulate on the positive side until top and bottom surfaces are equal in terms of charge. And it'll look like this: discharge, 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 lights up the lamp, and boom, it stops because all the charge is used up. Now, discharging a capacitor, we have to make sure we are very careful how we do this. And if we don't have a resistor in the way, if there's no resistor in this current path for discharging, the discharge of the cap can be very quick. It happens almost instantaneously. And that's that we want that instantaneous high power discharge to drive our camera flash. So as all of you have some kind of a cell phone, okay, some kind of a cell phone, some of them may be built in with a camera. And if you got a camera, it probably has a flash built in. And so you take a picture with your cell phone and it lights up the flash. Well, guess what? There is a capacitor built into your cell phone. There is this circuit built into your cell phone. So as this circuit's built into your cell phone, what happens here is, because there's no resistor in this current path from the capacitor to the flash on your cell phone, the discharge is immediate. The purpose of the resistor is to slow things down, but we don't want to slow things down. We want that fast, high power discharge so that we have enough energy to be able to light up that flash and give you a nice flash picture. So this is one very practical application of a capacitor. And there's one more slide after this. Okay, so we're going to discharge. Here we go. And it flashes until all the charge is gone, and then no more flash. Do it again, close the switch, electrons flow through it, light up the camera flash, and then capacitors discharge. Okay, now we can continue. And so in this slide 10, it goes to describe the inner workings of the capacitor with currents and such. You can read that. And that takes us up to page 11. So that's one of your videos, okay? If I come back up to drop this down just a touch, and go to here. Let me get my Excel back up. Here we go. Here's my Excel. If we go to the next one, capacitor values, Control C, and let's come up here. Paste and go.
Capacitor values. A capacitor consists of two plates separated by an insulating material called the dielectric. Capacitors store energy in the form of an electrostatic charge. Capacitors are assigned a numerical value called the farad. The number corresponds to the amount of charge the capacitor can store. The greater the farad value, the larger the charge it can store. Even though the farad is the basic unit of capacitance, it is seldom used because it's an extremely large amount of capacitance. A more common unit of measurement for capacitors is the microfarad. which is abbreviated the following ways. These abbreviations are listed on schematic diagrams and are printed on the case of the capacitor. Capacitor values are also commonly expressed in picofarads. That unit is abbreviated in the following ways. The value of a capacitor is determined by the following three factors: area of the plates, distance between the plates, dielectric constant, which is based on the material that the dielectric is made of. The value of the capacitor can be calculated by the following formula. C equals K times A over 4.45 times D.
I won't have you do that calculation. What's more important is when you physically look at a capacitor that you can identify, here's Mr. Lau, 25, 5 p.m. Wait. All right, so what's more important than calculating this is the understanding that the value of the capacitor varies depending upon several parameters. One of the parameters that's discussed is surface area, another is the distance between the plates, and another is the dielectric material, because the material we use for the insulator has a tremendous bearing on the properties of the capacitor. So if I go to, for a moment, let's see if I have it here. Let's go to here and go to here, Delmar. Textbook, waiting for textbook. Okay, so there's our textbook, and specifically on Lau, he was on, and then he maybe, oh, yeah, so Wenbin, you're connecting with your cell phone as well as with your computer. That's fine, welcome. So in chapter 20 in capacitors, your textbook does an excellent job of discussing many of the characteristics that we encounter in a capacitor. So, oops, let's go to here and let's go, if I can do a page down. All right, so capacitors, this goes to show a similar illustration to what it is that you've seen. Let's scroll gently. Now the capacitor symbol can be curved on one side and it can be straight on the other side. If it's shown with, instead of having a pair of parallel lines, that means the capacitor is polarized. A pair of parallel lines means a non-polarized cap, but a curved line next to a straight line here indicates this is a polarized cap. And in this illustration, how can you tell which polarity is positive, which polarity is negative? The one that's a straight line is considered the positive side of the cap, and the one with the curve is considered the negative side of the cap. So this would be characteristic of your electrolytics. Otherwise, your ceramic capacitors are going to be a pair of plain parallel lines. And in the last parts that you were given one of each of those parts. So in your parts bin, yeah, here we go. You were given a non-polarized cap, and the non-polarized cap is demonstrated with this particular guy that I'm holding up to the camera. So you all have one of these. This has no particular polarity. You can wire this up with either wire connecting to the circuit and it'll work just fine. Now, an example of a polarized cap will be, example of a polarized cap. I think, do I have one here? Do I have one here? Will look like a canister, will look like a little soda can, and it'll have a white stripe. There'll be some very clear markings as to what polarity is which. So the textbook does an excellent job of describing the electrostatic charge and what happens. It describes the type of dielectric materials that can be used in the construction of caps. Now, there's a lot of insulating materials. Dielectric, bakelite, mica, lucite, but there's no pure water, but it just goes to list some of the insulator characteristics of them and how they compare. But the most common ones used for capacitors will be some sort of a ceramic or some sort of a mica or some sort of plastic. A dielectric constant that goes to talk about this, and the calculation, the formula you saw a moment ago. I won't hold you responsible for calculating capacitance, but this you will be held responsible for, and you'll see these on your final examination. So capacitors in series and capacitors in parallel. I had a YouTube video on that to describe how to do the calculations of that particular exercise. And if I go to here and go to our friend YouTube, and then you go to look up, when YouTube comes up. The computer works slower when I've got Zoom working in the background. All right. So once on YouTube, you type in my name, Frank Coe, and then you'll find that I have a video channel, and you find the one with my friend Lisa on it. There evidently happens to be more than one Frank Coe. And boy, the YouTube sure is taking a while because Zoom is online. So be patient with this. I wanted you to see where we had put. This is an ungodly long time. Let's try this again. YouTube. Maybe this one will work faster. Who knows? Nope, not working much faster. Okay, doesn't matter. Okay, something's coming up. Anyway, it's still thinking. Let's get back to your textbook. So on your textbook, you were shown how to do these calculations of these fellas in series and these fellas in parallel. So when they are in series, unlike resistors, you don't add the capacitor values together. If you wanted to find a total capacitance of these three in series, you use your reciprocal formula as shown here. Or you could use a shortcut if there's only two capacitors, product over sum, but that applies only if there's two caps. If they are in parallel, the total capacitance is shown here with this formula, that they are the sum, okay? That's in your textbook, and let's go ahead and scroll gently. Hello? Is this gonna work for me? No, let's try this. No, something is definitely not happy here. YouTube is, I'll just shut it down, evidently holding things up. Back to your textbook. Okay, so what I want to show you here is, after all of this, the most important part of this chapter is this: capacitive charging and discharge rates. That's really, really important. 20-7, unit 20-7 and 28 go to show how the capacitor charges and how the capacitor discharges. So what you happen to have here are, in this particular illustration, and I'll magnify this, and I will go ahead and let's see. Let's make this full size. Okay, and make this bigger. So is that nice and visible on your screens? What it is that you've got on the bottom is something called time constants. Now, these are intervals of time, and there's a way of calculating what this interval is. With capacitors, it is an interval that is calculated by R times C. So if I have an R and I have a C in the circuit, then the value of R times the value of C will give me this interval of time. And it takes 5 time constants for the capacitor to reach full charge. In other words, when we first close that switch, there is no voltage on the cap, and that's why this blue line is down here at 0. So it's at 0 with respect to time, and it's also 0 with respect to voltage. Watch what happens in the very first time constant. In the very first time constant, from here to here, the capacitor will charge 63.2% of maximum. If the total capacity is 100 volts, let's say we had a 100 volt source. Well, what is 63.2% of 100 volts? 63.2 volts. So it charges that percent of the maximum, so it charges up to here. It's pretty quick. In the next time constant, take a look at what's left. What's left is not quite half. And so what happens is it charges another 63.2% of its maximum, and it reaches this point, which gives us 86.4. And now the capacitor is here. But notice that the curve between the first time constant and the curve between the second time constant has reduced. This is a very sharp curve in the first time constant. In the second time constant, it's not as sharp. It's starting to reduce its sharpness. And the same thing happens once we are here at time constant number 2. What happens between time constant number 2 and time constant number 3? Look at where this is. Of this, we have this much more to go. How much more will it charge? What percent of what is remaining will it charge? 63.2%. 63.2% of what's remaining will bring us now to this point they call 95 volts. It's 3 time constants now, and it becomes gradually less and less and less. So in theory, the capacitor never ever reaches 100 because it's always charging 63.2% of the maximum at each interval. But we say, as human beings, for all practical purposes, after 5 time constants, it is so close to 100 volts, 100%, that we will say that it has reached full charge after 5 time constants. This is the curve of voltage for the time constants. The curve for the electron flow is opposite this. The curve for electron flow was demonstrated in the previous screen with the video, showing that the current started at maximum first, and then it gradually went down to 0. This is very significant, and let's see if they show that. No, this is a discharge curve. So if we go to discharge the capacitor, again, it doesn't come straight down. There is a time interval involved. So it takes how many time constants for this to reach a full discharge? 5 time constants. At each interval between 0 and 1, between 1 and 2, between 2 and 3, 3, 4, 4, and 5, at each interval, the capacitor will drop 63.2% of its maximum. So at the first time constant, it drops to here. And then in the next time constant, it drops another 63.2% and will reach this point. And then the next time constant, it drops another 63.2% of what's left until we finally get to a curve like this. So the voltage charge curve looks like this. It is a rising exponential charge, very steep at the onset, gradually sloping to a flat line. The discharge is also an exponential curve, rapid discharge initially, but gradually tapering off until we finally reach a 0. The discussion on time constants is shown here. The symbol called tau, this little symbol here looks like a cursive T, a lowercase cursive T. It's actually a Greek letter. It is T-A-U, tau. And it is R times C, whatever the value of R is in the circuit times the value of C will allow us to calculate that tau. So here in the book we're shown a resistor and a cap, and the tau, the time constant in seconds, is the resistance ohms times the capacitor in farads. So here's TAU, tau, and that represents the amount of time for one time constant. And how many time constants before it reaches full charge or discharge? 5. Okay, 5. All right, so now let's go ahead and see what happens when we have a example. And here the example is you're given a 50 microfarad cap. So pull out your capacitors, pull out your calculators, I'm sorry. Pull out your calculators. And we're not going to do this using decimals because that's for middle schoolers. 50 microfarads and a value of 100 kilo. So in your calculator, you will type in 50 exponent negative. That'll give you negative. Now, micro is what power of 10? Do you remember? 6. So 50 exponent negative 6. You type that in first. That's your 50 micro. And then you're going to multiply that with 100 kilo. So 100 exponent, and kilo is what power of 10? 3. So multiply that. And then your calculator shows that we will have how many seconds? It should show 5 seconds on your calculator. And so one time constant, 1 tau in this particular example is 5 seconds. How many tau does it take for the cap to reach full charge or full discharge? Will be 5. So in order for you to determine the time for it to reach full charge will be 5 times 5 seconds each, giving you a total of 25 seconds, which is the calculation shown in the textbook. Does that help you understand part of the calculation for calculating tau? It's simply a value of R times C, okay? Now let's go ahead and take a look here. Here's another example. Are there any questions so far? Okay, so if we, says how much resistance connected in series with a 100 pico capacitor will give it a total charge time of 0.2 seconds. Okay, so 0.2 seconds is called what? It's defined here as total charge time, yes? Total charge time is how many tau? How many tau makes total charge? 5. So what we want is the value of 1 tau, yes? So if the total charge time is 0.2, let's go ahead and take 0.2 divide by 5. That means 1 tau. So go ahead, take 0.2 and divide by 5, and you're going to calculate 1 time constant. What does your calculator show you when you type in 0.2 and divide by 5? Andrew, what do you have? .2 divide by 5. Turn off your mic or turn on your mic. Your microphone's on. I can't hear your answer.
40.
You want to look at your calculator a little more closely?
I put 0.2 divided by 5.
0.2 divided by 5. And what's your calculator show you on the far right-hand side of the screen?
A milli.
So this is time. So if we divided 0.2 seconds, the units are seconds, and you divide by 5, that means each time constant is 40 milliseconds, yes?
Yes.
So the full answer is not just 40, it is 40,
40
recalculate milli,
milliseconds.
and the units are of time are seconds. So 40 milliseconds is the actual time for one time constant. So if you have this formula here that tau over the capacitor value will give you the resistor value. So if you put in 40 milli up here and divide by 100 pico, so your calculator should already show 40 milli. And then you will simply divide that by 100 pico. So it's 100 and exponent negative. Now, do you remember what power of 10 is pico? Rolando, do you remember what power of 10 is pico? Negative what?
Negative 12.
Negative 12 is correct. So you put that in your calculator, negative 12, and then you hit enter, and then your calculator will show you what the resistor value ought to be. So if you were all successful in that, Gabriel, what did you calculate for the resistor value? What's your calculator show?
I'm trying to find my calculator right now.
Okay, Christian, what does yours show?
Got 400 not micro milliseconds.
No.
Megaseconds.
40 milliseconds. 40 milliseconds divided by 100 pico will give you
40 milliseconds divided by 100
pico.
Hold on, I did it. A second. I got 400 mega ohms.
400 mega ohms is correct. Is everybody else all right with that calculation? Pauline, you okay with that? Rebecca, you okay with that? Okay. Wenbin, are you okay with that calculation? Thank you, Rolando. Love it. Looks good. I appreciate that. He's holding his calculator up to the screen. That's great. All right. So yes, and so the stated answer in the book shows 400 mega ohms. And so this is just simply helping you around with the calculations. Now, applications for capacitors, you have polarized ones, non-polarized ones. These are non-polarized here. They have no marking of polarity on either end. And then we do have polarized ones, and they would be clearly marked one side positive, one side negative. This goes to show the construction of a capacitor, another construction of the capacitor, how they work. This is all very interesting. Let's continue, more on construction. Variable capacitors. This is very interesting. We can actually change the value of capacitance by turning a knob. And this one is an example of a variable capacitor. So here we have many conductive plates that are stationary, and we have many conductive plates that are part of a rotating wheel, and it will move. And let's take a look here if I can find us a nice, let's see, is it working any better now? Okay, while that's thinking, I'll go to Google, and variable capacitor. Capacitor for AM radio. Okay, this is a good one. And do I happen to have one that shows ganged variable tuner? This is a good start. And let's see if there's other ones that might be good also.
आज के इस वीडियो में मैं आपको गेन कैपेसिटर के बारे में बताऊंगा कि ये गेन कैपेसिटर क्या होता है और इसको हम लोग कहाँ पे इस्तेमाल कर सकते हैं और इसको हम लोग किस चीज़ के लिए नहीं इस्तेमाल कर सकते हैं। देख ले, हमारे पास जितने भी कैपेसिटर होते हैं, ये कैपेसिटर जो होते हैं ये नॉर्मल कैपेसिटर होते हैं, इनको फिक्स कैपेसिटर कहते हैं। यानी इनकी वैल्यू जो है ये चेंज नहीं हो सकती है जब भी हम लोग इसको सर्किट
There, now you've understood it all. I don't know what language he was speaking, but anyway, he has electrolytic capacitors there. I was hoping for a little better picture of a variable capacitor than this particular guy. It's fascinating to see how a variable capacitor works. It really, really is very interesting. But in any case, since I can't easily show that to you, it's all right. Yeah, skip that particular one. It shows the demonstration of a variable capacitor used, but I wanted to see the inside of a variable capacitor. Here, let's see. Variable capacitor animation. That's very good. Yeah, this is great.
Now I will give an overview of construction of different capacitor. For that, we will first discuss the basic construction of
Now let's see if we have, here we go.
connected with the capacitor is rotated. The movable set of plates rotates and overlapping area as between fixed and movable plates vary. This causes variation in effective cross-sectional areas of the capacitor. The capacitance varies when one is the knob attached to the air capacitor. This type of capacitor is generally used to tune the bandwidth of a radio receiver. Next.
Okay, so I can also illustrate it this way. Let me stop that share for a moment. And let me go to here. I think we can do it this way. Good. And I will go ahead and click on this. And let's do speaker view. And if you could turn off your microphones for a moment. Yeah, turn off your microphones, because if there's any background noise that happens, all of a sudden your face and your name pops up on the screen. And then it kind of disrupts what other people are seeing in the recording. So Rolando, could you make sure your microphone is off, please? Thank you, perfect. All right, so here's an illustration of a pair of plates. Let's say we have these plates. These are the plates of a capacitor. And part of what determines capacitance is surface area. Well, if this is just a plate and this is a plate and I don't have them near each other, I have no surface area that forms a capacitor. The capacitor surface area we're talking about is the area where the capacitors overlap. So if I do this, now I can see that my overlapping area is this part here that's overlapped. And so here, let's do this as 1/4. Boom. All right. So what is the area that is overlapping? Isn't this 1/4 of the large post-it? That is the amount of capacitance that I have when this is the surface area. Now, if I change this, watch this. If I change this and I go here, now what is my overlapping area? Half of the size of the plate. When I increase my overlapping area, I will increase capacitance. So I will have more capacitance here. I will have less capacitance here. I will have maximum capacitance when the two plates are imposed upon each other. This is the maximum capacitance for this particular capacitor formed of two plates. So how does the variable capacitor work? The variable capacitor is fascinating. There is a pivot point right here underneath where my finger is. And when we go to turn the knob on a radio, we're actually rotating one part, we're actually rotating one of the plates. And so what happens is when we have the knobs rotated this way, all we have are plates, other plates behind this that are same size as this. We may have 10 of these, and they're all in parallel with each other, and that has a certain amount of capacitance. I have another 10 fastened onto my shaft, which I'm going to be rotating. And as I rotate this other 10 will go in between the first 10. And as it rotates, rotates, and rotates, now can you see an increased amount of surface area where one set of plates is interacting with another set of plates, and I've increased the area, and now I've also increased capacitance. And if I rotate further, and I have both sets of plates superimposed on each other, now I have maximum capacitance. That, my friends, is what is happening with this variable capacitor, this tuning capacitor here. As I'm rotating the shaft, one set of plates is fixed, and there's space between them for this other set of plates to go in between. As we go to rotate the shaft, this is what happens. That set of secondary plates comes down in between the first set, and where they overlap determines their new value of capacitance. So surface area is a big deal in determining capacitance. What else is a big deal determining capacitance is the dielectric that's used between the plates. Here, the dielectric is air. And then what else is a determining factor is a distance between the plates, because the more distance I have between the plates, the less capacitance I have. If I have these plates really close to each other, intimately close to each other, but still such that I can move, I'm sorry, you're not seeing what I'm showing. I apologize. Let me share this with you. Okay, back to this illustration. All right, so this goes to show the variable capacitor with one set of plates that is fixed. This goes to show another set of plates that will interleave with the first set that is movable. So by rotating this shaft with the knob on your radio tuner, I'm rotating this set of movable plates. And as I'm rotating in a counterclockwise fashion, watch what happens with this upper set of plates. It will rotate, and it will rotate, and now it's come down, and where the secondary set of plates have come down, there's now increased surface area between the first set of plates and the second set of plates. That's what changes the capacitance in this variable capacitor. That by changing the capacitance, we're using this in a tuning circuit to change our radio frequency. So we can listen to boom chukka hi-fi with the knob in one position. We can listen to classical with the knob in the other position. We can listen to country, western, bluegrass with the knob in a different position because the capacitor has changed, the radio station has changed. This is a key fundamental part of tuning circuits, especially for like AM radios, okay? So wanted to show you that. And here is a real one showing one set of fixed plates, and sandwiched in between is another set of plates that will interleave depending upon how the knob is rotated. Okay, let's move on further. This goes to show your a capacitor with a diagonal line, or any electronic component with a diagonal line, means that it is variable. And here we have a straight line with a curve. This is an electrolytic capacitor. This one is shown with an arrow. So the arrow is another way of showing variable. So this is variable, as long as you see an arrow in here. Capacitor markings. Capacitor can be marked with color dots. They could be marked with numbers. They could be marked with letters. And there's a nice reading there about that. We won't be concerned about the color dots and how they mark things depending upon the capacitor, but I will talk to you about this. Okay, here we go. When you see digits that are on the capacitor body, that will allow you to determine what the capacitor value is. So, for example, if you were to see this, and let me go ahead and get this guy set up. So, and let's go to unshare this screen. And okay, we're here. Okay, so let's talk about this. Reading cap values. So if the capacitor the little flat ceramic disc is with a capacitor. And let's say you see a number on here that is 104. The one that was shown in the textbook was, I think it was a 105. Let's see what the textbook shows. Yeah, that was a 105. We're going to put in 04 in contrast to what you have in your textbook. So when you see these three numbers, it's very easy. There's a method by which you are able to determine the capacitor value. And the first digit is your first digit of the value. So first number equals first digit of cap value. Second number equals second digit of cap value. Third number equals number of zeros. Number of rows, and then number of zeros before PF, which is picofarads. And as a reminder, pico is 10⁻12, okay? So let me show you how we interpret this guy. If you see a marking and it shows 104, what is my first digit? My first digit is a 1. If my first number is a 1, it represents the first digit of my cap value. So this would be interpreted this way, as a 1. And then the second number is a 0. It represents my second digit of the cap value. So it's going to be this guy here. And then the third number represents what? The third number represents number of zeros. And how many zeros is represented by the third number? 4. So I'm going to write down 4 zeros. 1, 2, 3, 4. Now I've got 4 zeros. And all of this is in what units? All of this is in units of picofarads. So I'm going to write picofarads over here. And so what this means is we happen to have, guess what? 100,000 times 10 to the -12 farads. Wow. Well, we know that we don't key anything into our calculator or write down any answers unless they are proper engineering notation. And this has got 6 digits here, so this is certainly not proper engineering notation. Try this right now. In your calculator, key in 100,000. So just on your calculator, key in 100,000 EXP, change sign 12, and then hit the equal symbol and see what your calculator displays. Calculator should display. And the question goes to, let's see, Pauline, what do you got?
I got 100 nano.
Yes, you would have received 100 EXP -9, and you know -9 is written as 100 nanofarads, okay? Now, capacitors are very interesting. What we have here, this value that you've just calculated is proper engineering notation. We've learned this as being such since the second week that we were together. Capacitors, however, do not conform to proper engineering notation. Capacitors, however, are standards at very specific units. So standard cap units will be equal to farad, will be equal to microfarad, and will be equal to picofarad. Those are the standard units. In capacitors, we would not write our answer in nanofarads or gigafarads or millifarads. These are the standard values: farads, microfarads, and picofarads. So what happens is this is actually equal to 0.1 microfarads. Okay, they are the same value. 1.1 microfarads is the same as 100 nano. So I want to point out the distinction to you. In case you happen to see this, you'll say, wow, in the literature, either Coe put down an answer, or in the literature, some book printed a decimal point, some kind of microfarads, or a decimal point, some kind of picofarads, something. How come they're not using proper engineering notation? Is because the world, it's not just the US, but the entire world standardizes capacitor values at these increments, all right? But for our calculations, we'll just go ahead and use the 100 nanofarads. That's perfectly fine because it conforms to what we've learned since the first, second weeks that we were together. So is everybody okay with the manner of how we read cap values? Whatever numbers are shown here, first number represents first digit, second number represents second digit, third number represents what? The number of zeros before what? Before writing down lowercase p, capital F, which stands for what? Picofarads. And picofarads is 10 to the power of negative 12. So this 104 becomes a 10, followed by 4 zeros, followed by picofarad. And then you put this into your calculator as 100,000 10 exponent negative 12, and let your calculator spit out the appropriate engineering as being 100 exponent negative 9, which you would understand to be 100 nanofarads. Are we okay with this so far? Now, let's go back and take a look at the example that was shown in the book. The example that's shown in the book was a number 105. So a number 105 cap. How do we play with this particular guy? Okay, so what is the first number? What is the second number? And the third number represent? So first number represents first digit. Second number represents second digit. Third number represents number of zeros before we write down picofarads. Okay, so if we go to interpret this particular guy, we have a 1 followed by a 0. And then we're going to write down number of zeros. So the number of zeros in this case is 5. So we're going to write down 1, 2, 3, 4, 5 zeros. Then followed by what? Followed by picofarads. So by looking at this number, have we properly interpreted as this so far? Hopefully so. The pico is 10 exponent negative 12. So if you go to punch this into your calculator, this should work out to be 1 microfarad, yes? Gabriel?
Yes.
Yes.
Yeah, it does.
Yeah?
Yes.
Okay, and this should give you 1 microfarad. All right. So now I've got something more interesting for you to do. Suppose you have a cap value that's this guy right here. Cap value is going to be a number 474. Go ahead and interpret a 474. And I will call upon names in a moment. First number, second number. Third number is first digit. Second number is second digit. Third number is number of zeros before we have picofarads. So, Mr. Lau, Wenbin, help us out with this. How do I start writing my capacitor value? How do I interpret this as being some number of farads? What's the first thing I do? Can you give me the first digit, sir?
First digits. Oh, I can't
Turn off your mic.
That's more. 474.
For this guy right here.
474, one digit.
Wenbin?
Yep. You hear me?
Yeah, I'm looking for the first digit. What is my first digit?
474. Is that it?
Well, 474 is the number that's printed on the capacitor. Your job is to interpret that based on everything we've done here in the past 3 examples.
Interpret. I can't hear the answer. Huh.
Andrew, do you have my first digit?
Yes, I do.
What's my first digit?
4.
First digit is a 4. First number represents first digit. It's a 4. My second number, let's take a look. Christian, what do you have?
7.
7. Okay, so Wenbin, coming back to you. How many zeros am I going to write? The third digit tells me how many zeros. How many zeros am I going to write?
1.
No, sir. What's it say here?
4. Yeah,
This,
4.
4 and a 7. So 4 and a 7. This 4 tells you 4 zeros. 1, 2, 3, 4. Now, Kyle, what do I have to write down after these 4 zeros?
The picofarads?
So I write down lowercase p, capital F, yes?
Yes.
Picofarad is what power of 10, Rebecca?
Negative 12.
Negative 12. So if you key this into your calculator, what is the value that your calculator spits out? That question goes to Andrew. Andrew?
It is 470 .00, I guess, but it's to the -9.
And what engineering prefix -9?
-9 is a nano.
Yeah, exactly. So your calculator did show 10 -9 farads, which we will write down as lowercase n, capital F. So are we okay with how to interpret a capacitor value based on some code that is printed on the outside of the capacitor? Everybody
Yes.
good with this? Based on this example that we started with at a 104, based on this as a 105, based on this as a 474. So everybody okay with that? So far, so good? Okay. Now, most capacitors are not a mystery. Most capacitors that you're likely to encounter, like these, electrolytics. Here's an electrolytic capacitor, and here's another electrolytic capacitor. And so on the electrolytic capacitors, it turns out that they happen to have a printed value right on the body of the capacitor. And it's, let's see if I can hold it steady so that the camera can focus on this. Let's see, get some light on this. Can we have any kind of light on this and then try to focus and rotate it? And you can almost make out, I'll try the focus again. Aha. Can you see a 100 microfarad written on there? And then it has 25 volts. Okay.
Um,
I'm surprised. Wow.
Yeah.
There we go. Pretty good. Pretty good. Anyway, let me hold it up to the light a little differently. Do a focus again. Turn off your mics, please. And right there, if I catch the light just right. Anyway, it's a little, yeah, you have 100 microfarads. So it's printed on the body of the electrolytics because the electrolytics are large enough. And then they're also, what else is also printed on the electrolytics is the white band that shows the negative side of the capacitor. So there's that white stripe on the body of the capacitor, and it happens to be attached to this wire, which is the negative wire, and then the longer wire is the positive wire. So that's how you, the electrolytics are large enough that there's no mystery in terms of how to determine what their value is. So, but the ceramic ones, the disc ones that I showed earlier do need to be interpreted. All right, so now let's move on. Let's go ahead, put this away, put this away, put this away. All right, we need to talk about time constants, and we need to introduce our friend Eli the Iceman. So let me go back to share for a moment. Share, and go back to the textbook and share. Okay, so on here, capacitor testing, this is all good, all good, all good, all good. And then there's all of this. Okay, so I just want to go to the time constants. Come on. Here we go. These guys right here. This is gold. So go ahead and do this. All right. And this curve, be mindful of. And what I'm going to do is set this up so that I can do new notes for you. Mouse on computer. Stop this, go here, focus. Okay, so now that's focused on that plane, and RC time constants. So for RC time constants, let's say I happen to have a circuit. So this represents a switch, S1. This represents C1. This represents R1, and this represents my voltage source. And let's go ahead and make this not so challenging. Let's go ahead and make this a 10-volt source. And let's go ahead and give a value to the resistor. And let's say the resistor happens to be equal to 470 ohms. And let's say the capacitor happens to be a number 324. Okay. And so what we need to do is, first of all, C is equal to some kind of farads. And then we're going to calculate this here, TAU, and that's equal to time constant. And time constant is going to be calculated as the value of R times the value of C. And that's going to be equal to some number yet to be determined. So we have a little bit of work to do. So get your calculators ready. And as you get your calculators ready, we'll go ahead and make these calculator exercises here. First thing we need to do is to interpret the 324. What kind of value is it in terms of capacitance? So, Rebecca, 324. So how do I interpret this? This would be a what? First digit is a?
3.
3. Second digit is a?
2.
2. And then the, how many zeros?
4.
4 zeros, followed by what symbol?
Picofarad.
Pico, and then the units are in units of farads. Okay, so this interprets to be 320,000 picofarads, but we know that that's not proper engineering. So what would you write down in here as an answer that would be in proper engineering notation, Rebecca?
B.
I didn't quite hear it all. We still didn't quite hear it all. Yeah, give you a moment, pop that into your calculator, 320, 10 exponent negative 12, and your calculator spits out what?
320 nanofarads.
Perfecto. So 320 nanofarads. Okay, is everybody all right with that interpretation? Any questions on how that's interpreted? Okay, the next thing we need to determine is this thing called time constant. And time constant is given as this symbol, looks like a cursive T or maybe half of a pi. It's called tau, it's a Greek letter, and tau is calculated as the value of R times C. So the value of R in this case is 470. The value of the capacitor we have to key in as 320 nanofarads. So this multiplication exercise is going to be 470 times 320 exponent, and this is a negative, and nano was 9. So we're going to do this keystroke sequence. 470 times 320 exponent negative 9 equals. So what does that calculate to be? Let me go ahead and do this with you. Question will go to Pauline. Do you happen to have that yet?
I'm getting I'm getting 100.
Yeah, so go ahead and key in 470 times 320 exponent negative 9 for the nano, and then hit equals.
Did you hear me? Sorry.
I didn't hear that fully, no.
Oh, sorry. I am getting 150.4 microseconds.
Okay, as my calculator does the same. So I have the 470 times the 320 exponent negative 9. I get 150.4 exponent negative 6. And so that was called out correctly as being 150.4 micro is the negative 6, and tau in units of time is not in farads, it's not in ohms, it's not in volts, it's not in amps. Time is measured in what units, my friends? Is measured in seconds. And seconds is shown with a lowercase s. It is not a capital S. Capital S is a unit of conductance called Siemens. So it's a lowercase s. So is everybody okay with one time constant being 150.4 microseconds? So the next question to be asked will be this: time for full charge equals question mark. And how do I determine the time for a full charge? Christian, Mr. Cortez, how do I determine the time for one charge?
Is it the 63% thing?
No, because if we refer for a moment, and let me help us out, refer for a moment back to
divided by 5.
back to almost, you're close. Take a look at this illustration here. This illustration is what we're going to be drawing in a moment. So the capacitor starts off with nothing at the very beginning in terms of voltage down here, 0 in time and 0 in volts starts here. The moment we close the switch, it'll start charging, and then it'll charge until it reaches full charge. But how many time constants are shown here on the bottom is what I want you all to focus your attention on. So we have 1, 2, 3, 4. How many tau? How many time constants to reach full charge?
5 time constants.
5. So the process is to do this. We know it's, so the time for full charge will be equal to tau times 5. So whatever we calculated for tau up here, the 150.5 microseconds, is going to be multiplied by 5. So 150.4 microseconds times 5 will give us this number here. I will just simply do times 5. And the answer to that one, Gabriel, what do you calculate? 150.4 micro, which is 10 exponent negative what? Gabriel, turn off your mic. Turn on your mic, I'm sorry.
-6.
-6, so 150.4, 10 -6 times 5. What do you calculate as your time for full charge?
150.4
micro will be multiplied times 5.
Oh, okay. 150.4.
Micro, don't forget the micro, 10 exponent -6.
752 microseconds.
Okay. And my calculator verifies your calculation is correct. So 752 microseconds. That's the time it takes for this capacitor to reach full charge based on the circuit that I have here of 470 ohms and a number 324 cap. So let's show you what happens here graphically. And I'll try to do this to the best of my ability this way. I'll go ahead and draw an axis going like so, and I'll go ahead and draw an axis going like so. 2, 3, 4, 5. Okay, so something like that is good. And I'll use these graduations here. So this is 0, this is 1, 2, 3, 4, 5. So this axis represents time in units of tau. This axis here represents two things. It will represent a V for volts, and it will also represent I in amps. It'll represent voltage and current, okay? And so let's see what happens with this. If I have a maximum, and let's see, let's do. Okay, so if I graduate this one this way, okay, so this will represent 2.5 V, 5 V, 7.5 V, 10 V. If I just graduate it this way, my maximum line would be somewhere around here. Somewhere around there would be my maximum, okay? So this would be max. And, oh dear, smudge, oh well, can't happen, can't help that. Let's go ahead and do this, Go ahead and do this. Go ahead and do this. Go ahead and do this. And go ahead and do this. All right, so there's my intervals: 0 tau, 1 tau, 2 tau, 3 tau, 4 tau, 5 tau. And let's go ahead and plot what happens with respect to voltage based on the textbook illustration. My maximum voltage is 10 volts, yes? And in the first time constant, what happens here is this. Let's go ahead and pop this in here this way. In each time constant, the cap will charge / discharge. Would somebody turn off their microphone, please? Because there's some background noise. Thank you. So in each time constant, the cap will charge discharge 63.2% of the remaining value. That is a very important characteristic of logarithms and how this all behaves. And we won't get into a discussion of how the logarithm is derived and how the exponential curve comes about. Just accept that this is a simpler way of determining what these numbers are going to be. 63.2%. What is 63.2% as a decimal? Isn't 63.2% as a decimal going to be 0.632? Is that right, everybody? Okay, so here we go. We're going to determine initially our voltage is going to be here. It's in green. There's my green dot. And what happens in the first interval between 0 and 1 tau? Within 1 tau, the amount of voltage that the cap will charge will be 63.2% of what? Of the remaining value. Well, what's remaining, if we're starting at 0, what's remaining is the full 10, yes? So what you're going to do is you're going to multiply 0.632 times 10. So in first tau, 0.632 times 10 volts will give you what? 6.32 volts. And graphically, where does 6.32 volts sit? It's approximately right here. It's above the 5, so I'm just going to approximate a green dot right there. Is everybody okay with how we landed that first dot and how that number came about? Any questions how this number came about? This is presently 6.32 volts. Any questions on that?
Is that a 0.672 times 10 volts or 632?
This is 0.632 times 10 volts, which is same decimal that I wrote there in red, which is the same as 63.2%. Is that a little better there for you, my friend? I'll try not to write so small.
Yeah.
Okay, all right. But yeah, please don't hesitate to ask any questions. But are we okay with how that number came about? Okay, so here's the thing. Here's what's fascinating about all of this. If this is where we're at, how much is left? How much is remaining? How much is remaining is not the full 10. How much is remaining is going to be 10 minus 6.2. What's 10 minus 6.32?
3.68.
3.68, right? So what's left right here is 3.68 volts. That's what's remaining. So remaining, I'll do some darker ink. Remaining equals 3.68 volts. That's what's remaining. So what's going to happen in the next time constant? In the next time constant, so I'll write down, in second time constant, what we'll do is 0.632 is going to multiply the remaining value of 3.68, right? So 3.68. This is how much more the capacitor will charge. And mathematically, let's all go ahead and do that on our calculators. So we will take 0.632, and we're going to multiply that by 3.68. And your calculation works out to be what? Mr. Rolando, help us out here. What do you get?
Uh, 68.
I didn't hear an answer. Are you still calculating, sir?
Okay, I got 2.33.
Okay, so it works out to be 2.33 volts. Is that everybody gets? Okay, well, you can turn off your mic now. Or turn, yeah. And then, so does everybody verify 2.33 volts is what this calculates to be, yes? So 2.33 volts. Has to be something less than 3.68. So the 63.2% of this is this. Now, this tells you how much more the capacitor charged. So what we're going to do is we're going to add to this number, and we will get the new value of what the capacitor is now. So we are going to add this to 6.32. And the new value works out to be 8.65 volts. So our new point here will be here above the 7.5, and we will put this here, and this will be 8.65 volts. Are we okay with how that's calculated? And guess what? If we repeat this exercise for the third tau and the fourth tau, we'll do one more tau, okay. In third tau, what will happen? What will happen between the second and third tau is the cap will charge 63.2% of what? The remaining value. What is my remaining value if I'm currently up to 8.65? This will work out to be 0.632, and we're going to multiply it by what's remaining. Can someone tell me what this number will be? I will call on Andrew. Can you tell me what is the remaining? If I have 8.65 where the cap charges up now, my maximum is 10, how do I find what's remaining, the difference between these two numbers?
What's remaining? 1.35.
Exactly. It is 1.35 volts is what's remaining. Excellent. So when we go to do this calculation, we will go ahead, pop our calculator back in, and
I got 853.2 milliamps.
0.632, and we're going to multiply by 1.35. You almost called it out correctly. It's not milliamps. It's voltage.
Oh.
So you called out. Go ahead. You called out.
8 point, what was it? My calculator just cleared on me. What, 8.5? It was 8.5. 8.5.
Okay, everybody should have 853.2 millivolts.
Millivolts, okay.
That's how much more this will charge. Well, what are we going to do with this amount? We're going to shoot this up here and add to the previous plateau, because we have reached different plateaus along the way. The first plateau was 6.32 volts. The next plateau was 8.65. We have to add this incremental amount to the previous one. So we'll go ahead and do that. There's my 853.2 milli, and I'm going to add that to 8.65. Boom. What do I have? That will generate a new plateau of 9.50 volts. Is everybody okay with that value? 9.50 volts. Any questions how we determine that next plateau value, which will plot right about here, and that's 9.50 volts. Okay, 9.5 volts. So what happens, okay, without doing the mathematical derivation for the third tau and the fourth tau, we can do that. Basically, if you look at this, the dots, are we getting closer and closer? Ultimately at 5, we are so close to 5, we pretty much put our last dot right there. And if we go to connect the dots, we end up with an exponential curve that looks something like this. Here, 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 and here. This is how voltage charges over 5 time constants for this particular resistor and this particular capacitor. And how much time is that? Well, let's go ahead and analyze this again. We determine each time constant by multiplying the R times the C as 150 micro. So that means from here to here, I have 150.4 microseconds. From here to here, I have another 150.4 microseconds. Well, in total, how much do I have for the 5 time constants will be 150.4 microseconds times 5, and that will give me 752 microseconds for the total time for this to reach full charge. Is everybody okay with that curve, how it's drawn? Is everybody feeling comfortable about how these numbers are determined? And they're determined by the rate of charge of the capacitor based on this R value, the C value, and it can only go increments of 63.2%, but the keywords are what? 63.2% of the remaining value. Okay. That is the charging curve for voltage. What does this look like for current? Current is at maximum at the very beginning. I'm going to put a red dot for current. I'm going to write over here. Current is at maximum at the beginning. So the moment we close the switch, right here at 0, my voltage is nothing, but my current starts flowing immediately to start charging the cap. As the cap is charging up, the rate of current flow will decrease. So at what rate does the current decrease? Listen carefully. The current will decrease 63.2% of the remaining value. Check this out. If it started here at maximum And the goal is for current to go down to 0. 63.2% of this range from maximum down to 0 puts us at a red dot right about there. So the current will drop from here down to here within 1 tau. How much will the current flow drop in the next time constant between this point and 0? Well, what is 63.2% of this line? Something more than half. So I will put a red dot right about there. What will happen with current as it decreases further between 2 tau and 3 tau? Well, what's the remaining value? The remaining value is from here to here, this little short line. And 63.2%, little more than halfway down, puts us right about there.
So could you take these, you know how we times it by 10 at first, and then we got 3.68? So we would put that on the first one and then keep on coming down?
Yeah, we won't do the math to derive this, but I just wanted to show you that the current is an opposite curve to the voltage. Okay, that's the point I'm trying to show you. We won't do another set of math for this probably ever again. And then the next red dot is here, and then the next red dot is here. And so current will come down from a maximum to here, drop to here, go down to here, continue to here, and finally down to no current. So when this has reached maximum voltage on the green curve, when this reaches the full 10 volts on here, there's no more current flowing. So the curve goes down to 0. And that's exemplified by our previous here. And let me go back one. Not capacitor values, but I want to go to here and go to here and okay. So the summary of this that I want to get to is this. The summary I want to get to is the moment we close the switch, 2 things are happening. The voltage starts charging from 0 and after 5 time constants reaches the maximum. At the same time, the current starts as maximum and starts decreasing down to 0. And so as you observe what's happening in this illustration, what quantity is at maximum first? What quantity is at maximum at the end? At the very beginning, what quantity is at maximum first? Now, maximum is this line right here. So which of the, is the green line at maximum at the very beginning, or is the red line at maximum at the very beginning? Rebecca, what do you think?
The red line.
Rebecca?
The red line?
The red line is at maximum at the very beginning. Does everybody observe that? If this is my maximum line here at 10, at 0 tau, at the very beginning, current is at maximum first. And then after 5 tau, the current goes to 0, then what quantity reaches maximum at the end is voltage. So here we can make a very strong and profound concluding remark. The concluding remark that I want you to take away from all of this, what we want to conclude with is here. Current, so this is VIP. VIP stands for very important point. And I'll do this in red. Very important point is current leads voltage. Current leads voltage. Or you could also say voltage lags current. That's a very, very important point. Include this with, and I'll tell you why that's significant in a little bit, but you want to write that down. So this is what type of circuit? This is an RC circuit, because there's an R and there's a C. And we're talking about time constants. Time constants are the amount of time for a cap to rise or discharge 63.2% of a remaining value. And so if we work out all the numbers for this exercise, we end up with these two lines, a red line and a green line. And as you observe, from the beginning to the end, the quantity that is first is current, and at the end, the quantity that reaches maximum is voltage. And that allows us to make this concluding remark. Current leads voltage, or you could also say voltage lags current. What does lag mean? Lag means to follow behind. Okay? Is everybody all right with that so far? Next. RL time constants. And in an RL time, there is something called an RL. What is L? L is your inductor. I will have here, let's say I have a voltage source. I will have a resistor. I will have a coil. That's a symbol for an inductor. I will have a switch. Like so. And so this will be L1. This will be R1, this will be S1, and this will be VS. So here's an interesting property. Inductance property of building a magnetic field around a conducting wire, period. That's one definition of inductance. Inductance can be thought of as the property of building a magnetic field around a conducting wire. So with any wire, if I have our multimeter leads, for example. So here's a pair of multimeter leads. And if I were to hook this up on a battery pack, so here's my battery pack. If I were to hook that up to the battery pack and pop in the third battery and measure the voltage between these two, there will be current that is flowing through the red and black wires. The electricity will flow out through the black wire, the net electrons will flow out through the black wire, get connected to my voltmeter, like so, and then the voltmeter will read the amount of that electricity flow, and based on circuitry in the voltmeter and the electricity that comes back to the positive wire, it will make a determination how much voltage I have in the battery pack. You've done this many times with your digital multimeters to measure voltage. But one thing that we hadn't talked about is in any wire that carries electricity, there will be a magnetic field that builds around that wire. It's a property of we call inductance. So here we go. As a magnetic field is built around the conducting wire, we can concentrate that magnetic field by winding the wire into a coil. Okay, so a coil equals concentration of inductance by winding loops, of wires onto each other. So the coil allows us to concentrate the inductance simply by winding the loops of wires onto each other. I have wire. If I make a loop like so, the magnetic field of the first loop will interact with the magnetic field of the second loop and will increase this property of electromagnetism. And then if I do this with another loop, and I do this with another loop, and I do this with another loop, and I do this with another loop. So what I've gotten are the same size loops, the same as I can make it in this illustration. And if I have electricity flowing through this wire, because I've now wound this wire into loops and have these loops the same size diameter and have them intimately close to each other like so, I have increased the property of inductance where this is now a useful thing. By making loops of wire in this fashion, I've now created something called an inductor. The property is called inductance. Winding them into a coil concentrates that inductance. And by creating a device that is multiple loops, I have created something called an inductor. An inductor is an electrical device that we use in electronics very often. And it's shown in the schematic symbol as coils like so. And I'll show another illustration of them in a moment. But this is how an inductor is very easily made. Now, like capacitors, weren't there different characteristics of capacitors that determine their capacitance? Didn't we talk about the size of the overlapping area previously? If I have capacitors with only this much overlapping area, I only have that much capacitance. If I overlap the area by this much, I have more capacitance. If I overlap the area significantly, like so, I will have maximum capacitance. So the amount of area of the plates onto each other determines capacitance. What else determines capacitance? Was the distance between the plates. So if I have one plate over here and I have another plate very close to it, I have pretty good capacitance. But if I start separating this, the interaction between the plates is less and less. So the closer I can get these together, the more capacitance I will be able to achieve. And then the third component that affects capacitance will be the dielectric that's used in between. By the same token, we also have similar concerns with respect to inductors. So here I've made multiple loops of wires into a coil. So one of the key factors that determines capacitance is going to be the diameter of my coil. The smaller I make that diameter, the more concentrated the magnetic field will be. Did you hear that? The smaller I make the diameter, the more concentrated the magnetic field will be. Well, this is about a 1-inch diameter. So if I were to decrease the diameter to half of that, if I were to wind all of this, say, around a pen, for example, like so, like so, like so, like so, like so, like so, like so. Wow. Is my diameter now noticeably less than what it was before? Yes. So by making the diameter smaller, I am concentrating the magnetic field. Therefore, I am increasing the inductance of my coil. Another property that affects, in addition to the cross-sectional area, the diameter which gives us the cross-sectional area, is the spacing between the coils. If I have a loose space between the coils, and this has to be uniform, and I can't do this very well with this demonstration, but if I have space between the coils where the wires are, where the hoops are not intimately connected with each other, I will have less inductance. If I jam them up, one right next to the other like this, and there's no air gap between them, I will have maximum inductance. So two factors we've discussed so far that affect inductance. One would be what? One would be what? Question goes to Kyle. What is one factor that affects inductance?
How close the coils are together?
How close the coils are together is one. So if I pack them up, they're really close, I will increase capacitance. If I space them out, I will have less capacitance. What is a second factor that affects capacitance? Mr. Cortez.
The diameter of the radius of the coils.
The diameter of the coil. The radius is half of the diameter.
Yeah.
So the same idea. So by making the coil physically smaller, I am concentrating the magnetic field. So this coil wrapped around my pen, as opposed to the first one that I made wrapped around, say, an imaginary 1-inch object, this will have more inductance because we have more concentration of the magnetic field. There is a third factor. The third factor has to do with the material that we use in the core of the coil. In other words, if I put something in here, if I create this coil and I pull the pin out, I have air in here, yes? If I have air in there, that's called an air core coil, meaning the core of this set of loops is hollow, so the core is made of air. I can concentrate the magnetic field further if I put something in that core. And what's mostly done in the industry is going to be an iron slug, a rod of iron, because a rod of iron not touching the coils but placed inside the coils will concentrate the magnetic field even further and will affect the amount of inductance that you're going to realize for this coil. So those are the three things that affect the coil: is the type of material that is used in the core, the diameter, and then also how tight the windings are. And I'll go ahead and release all of this. So let us say that this guy is equal to, let's say, 270 lowercase m capital H. So the device that we're talking about, the actual device, is called an inductor. It has another name. It could simply be called a coil. It could also be called a choke. There's a descriptive, they're called chokes, coils, or inductors, okay? So those are the name of the devices. The units equals H, which stands for Henry, named after the famous scientist who advanced the scientific papers to the community explaining all of this. So it's named after Henry, just like ohms was named after Mr. Ohm, and watt was named after Mr. Watt, and volt was named after Alessandro Volta, and amps is named after Andre Marie Ampere. So this is named after Mr. Henry. So that's why we have a capital H for millihenry. Is everybody okay with 270 lowercase m, H, 270 millihenry? And let me give you the value for the resistor, and let's say the resistor is equal to 950 ohms. And this is also equal to 10 volts. Now, the time constant in this particular case is going to be an interaction between the L and the R, and it happens to be L over R. L over R. We're not multiplying in this case, this is a division. And so in this case is equal to 270 equal to 270 millihenries divided by 950 ohms. So that's 270 exponent, change sign, and Wenbin, milli is what power of 10, my friend?
You know about 10?
Yeah, what power of 10?
One to 700.
Milli is -3. And then you're going to divide that by 950, and that will be equal to the time constant. And the time constant has units, and we'll go ahead and calculate that in just one moment. So let me go ahead and pop this in here.
1,842.
This is a divide, my friend.
Yeah, divide.
0.270 and divide by 950. So what do you have, my friend? Mr. Wenbin?
Oh, I can see.
270 exponent -3 divide by 950.
2.842. 2,000. No, 2.842.
Wenbin, you should have calculated your times by now. What are you doing?
I would do the 2.8 or 42.
No, hit engineering on your calculator, pal. You have it in scientific notation, so you got to put it in engineering notation. So what is it in engineering notation? Yeah, your number, I see what you've typed, and what you've typed is not correct. So I wrote down here, and if you follow this, 270 exponent -3 for milli, divide by 950, you should end up with 284.21, and the units are micro, because it's a 10 exponent -6 on the calculator, and time is measured in seconds. That's what you should have. Okay, Wenbin and everybody? Any questions about how to calculate the one-time constant? So yeah, you're gonna need a little more practice, my friend, on utilizing your calculator. And I'll do it again, 270 exponent -3, and then divide by 950. And that's what we have. Okay, so practice that until you are confident and comfortable with making the calculator demonstrate the correct result. Any questions does anybody have on the time constant? Okay, so here's the next question. Time for full, and I'll use the word charge. It's actually an incorrect word to use, but conceptually it's not bad. So how long does it take for this coil to reach its full magnetic capacity? Will be how many time constants? It works just like the capacitor before, will be 5 tau. So mathematically, we will do 5 times the 284.21 microseconds. And I'm looking for that calculation. If you can give me the calculation, please, Mr. Rolando. Time for the full magnetic field to develop.
Okay.
Rolando, do you have that number?
Okay, it's 1.42
1.42 what?
milliseconds.
Okay. So if you all go through this calculation correctly, and I'll take the chat off my screen because it's disruptive, you should end up with 1.42 milliseconds. So it's a lowercase m and a lowercase s. Is everybody okay with that time for the full magnetic field? So far, so good. Okay. Now, let me show you graphically what happens with respect to this on a time constant chart. So on a time constant chart, this is what we're going to have. I'll try to do this. Everybody turn off your mics, please. Thank you. Okay, so I'll try to do this a little larger.
All right.
Could you turn off your microphones, please? Thank you. Okay, so we happen to have something like this. Okay. And let's go ahead and space this out. So I happen to have 1, 2, 3, 4, 5. So one will be here. Next one will be here. Next one will be here. Next one will be here.
Apenas los compré, o sea, aquel lo tiene como 2 años más, aquel, ya me creció así de tamaño.
My friends, could you please turn off your mics? Thank you. All right. So, time constant chart. 0, 1, 2, 3, 4, and 5. This is time in units of tau. It's also in units of seconds if you'd like. Up here will be 2 values. Up here will be a value for V, and up here will also be a value for I. And let's describe what happens. Let's describe what happens when this switch is closed. The moment this switch is closed, the coil will resist current flowing. The current will not flow immediately. The coil behaves as if it's blocking all the current. And if it blocks all the current, it is as if this were infinite ohms in series with only 950. So here's the things to keep in mind for a coil. Initially, coil opposes change of current. So all voltage is across the coil. And I can demonstrate this very easily by drawing a separate little circuit on the side here. I will draw this. Here's a resistor, and here's the switch, and the switch is now in the closed position. And here is the coil. And here's another way that I'm going to draw the coil. Okay, that's another way to draw the coil. And so initially, there will be 0 amps. Because what? The coil wants to do what with the change of current? It wants to oppose any change of current. So if it opposes any change of current, whatever I start off with voltage over here, if I have 10 volts over here, do I have any current flowing through the resistor? No. I have 0 amps here. I have 0 amps here. What is my voltage across the resistor at this particular moment? My VR, isn't that equal to I times R? Is that right? Isn't that how I calculate the voltage across the resistor? What is my I at the very beginning? The current at the beginning is 0 amps. So my VR at the very beginning is going to be 0 times 950 ohms. So what is my voltage on the resistor initially? 0 volts. Nothing, nada. So in this circuit, do I have a closed loop, yes or no? The answer is yes. Here, do I have the ability for electricity to flow because I have a closed switch? The answer is yes. The ability is there for current to flow. However, a very unique characteristic of the coil is that it opposes any change of current. I'll say, well, wait a minute. What change are we talking about? Well, initially, if the switch was open, there is no current, yes? The moment we close the switch, is there a change of current that could occur? Yeah, current could start flowing. What does the coil do? It opposes that change. No current flows at 0 time. No current here means no voltage. Mr. Kirchhoff has to be happy. All the voltages in a closed loop have to add 0 volts. You know that from last week's discussion. Kirchhoff's voltage law says all the voltage in any closed loop algebraically has to add to 0. This is a negative, this is a positive, this is a negative, this is a positive, and this is a negative. Well, guess what? Initially, you will see you've got 10 volts right here. At the very beginning, the voltage is going to be green dot right there at the very beginning. At the very beginning, current will be red dot down here. So current is equal to 0 amps at the beginning. Your voltage is equal to max at the beginning, okay? What happens over a period of time is this. The current will be allowed to flow because the characteristic of the coil, it opposes initially it opposes a change of current, but slowly it lets the current start to flow. So in the first time constant, that current will flow 63.2% of maximum. In the next time constant, the increase will be to here. In the next time constant, then the increase will be to here. And the next time constant, this will be here. Finally, we reach maximum current at the end of 5 tau. And this curve looks like so for current. So I now have I max at 5 tau. It started off at 0, and after 5 tau, current reaches maximum. At the end of 5 tau, this becomes nothing but a straight piece of wire as far as DC is concerned. What happens with voltage? We said voltage started off at maximum. At the end of the first tau, this thing will drop 63.2% of the maximum to there. At the next one, it'll drop to here. At the next one, it'll drop to here. At the next one, it'll drop to here. Finally, it'll drop to no volts because this behaves like a bare piece of wire. I will go to connect the dots. When I go to connect the dots, I end up with this, and now V is equal to 0 volts at the end. Can you make a concluding statement similar to what we had before? We made a concluding statement before, very important point. current leads voltage or voltage lags current based on a capacitor circuit. Can we make a similar concluding statement here with respect to voltage and current? Rebecca, you want to give that a shot? What do you think you could summarize this with? And the wording will be similar to this. Something is going to lead something, and something's going to lag something.
Would
So
it be
what do
that voltage leads current and current lags voltage?
How about that? So voltage leads current and current lags voltage. Okay, turn off your microphones. That's excellent. And if I can squeeze everything into my frame here. Does everybody agree on that summary statement? The voltage is at maximum at the very beginning of our time constant analysis. And then after 5 time constant, then the current reaches maximum. So voltage is said to lead current, or conversely, we could say current is lagging voltage because it happens 5 time constants later. Any questions on that? And if we go to fill in our time, our time in here was, each one of these increments was 284.21 microseconds. This is another 284.21 microseconds, such that at the end of 5 time constants, this whole process took 1.42 milliseconds. Sorry, that's right at the bottom. Didn't mean to write quite that small and that far away. Let's see if I can make this just a little bigger. I think I can get it in the frame. Okay, that's a good frame. So how do we contrast, before we go to do the contrast, is there any questions as to what we've done here so far? How do we compare and contrast the green line of a coil circuit, an RL circuit? The green line starts at maximum and goes down to 0. Okay, it starts where? At maximum and goes down to 0. How does the green line work for a capacitor circuit? The green line starts at 0 and then works its way up to a maximum, yes? This started at 0, works up to a maximum. The green line here starts at a maximum and goes to 0. Take a look at how current behaves. Current started at 0 because why? The coil opposes a change of current, so initially the current 0 amps, 0, but after 5 time constants, that magnetic field will be such that it will allow current to flow. So the current starting at 0 after 5 time constants reaches maximum up here. How does this red exponential curve compare with the coil circuit compared to the cap circuit? Compared to the cap circuit, the red line starts at maximum and goes down to 0. So the concluding statements is going to lead us to a very profound mnemonic. What's a mnemonic? Who remembers what is a mnemonic? Pauline, you remember what is a mnemonic? M-N-E, mnemonic. You remember what was a mnemonic?
It's kind of like a rhyme that would make you remember the meaning of what it is that you're trying to remember.
That's a really good one. I like that
Just
definition.
like, Roy G. Biv is equal to the rainbow colors.
Yeah, I'll give you a simpler one, and I like this one because there's many different ways of putting together a mnemonic, but fundamentally it's a memory tool. So there's ways we can use rhymes to help memory tools. We can use acronyms. We can use abbreviations to help us in memory tools. So a mnemonic is fundamentally a memory tool. So the RC time constants and how this is derived and our L time constants and how this is derived takes us to a memory tool called, right here, black pen.
The Iceman.
Eli the Iceman. Okay? Eli the Iceman is a very profound mnemonic. It is a tremendous memory tool because it tells us the behavior of voltage versus current given these two types of circuits. So let's go back for a moment and review. So in review of Ohm's law. In review of Ohm's law, you remember that we had a circle, and in the circle we had a line and another line. And you remember what we put in the circle was a V up here, was an I, and an R over here. You may also remember in our textbook, the big Delmar textbook, it shows a different lettering. It shows an E, I, and an R. E stands for electromotive force, which is one of the definitions of voltage. So E and V are interchangeable. Anytime you see an E used in a formula, it represents voltage. Is everybody okay with that? And many books in print and in the literature utilize E, and our Delmar book utilizes the E. We've been using V simply because V is easier for people to think about voltage rather than E for electromotive force. So that being said, the mnemonic of Eli the Iceman, the E stands for voltage and the I stands for current. What do you think the C stands for? What do you think the L stands for? Here is a circuit that has an R, a voltage source, and a what? A capacitor. What letter starts with what capacitor starts with what letter?
C.
Here we introduced a coil with a resistor, RL time constant. What is the symbol? Letter symbol for a resistor is an R, letter symbol for a switch is an S, letter symbol for voltage source is V. What is the letter symbol we use for a coil? L. L is the symbol for inductance, okay? What are the units of inductance? What was the H? Henries. But the symbol for the coil is given as an L. So guess what, my friends? The L stands for inductor circuits, and the C stands for capacitor circuits. So here is your memory tool. Let me write this out for you. Eli the Iceman. This says for inductor circuits. This says capacitor circuits. And this says right here, since this letter comes first, this says voltage will lead current. Or you could say current lags voltage. Over here, since the I is at the beginning of the word ice, and it is in front of, before the E, before the voltage, here you would say current will lead voltage. Conversely, you could say voltage lags current. This is extraordinarily profound. As we get into the next topic of AC with these circuits, it's very important we remember Eli the Iceman. Eli the Iceman helps us remember what physical quantity comes before what physical quantity. And of these two sentences, the sentence that you really want to take to heart is this one right here. This one, right there, and this one right here. Which quantity comes first? Voltage leads current in a what type of circuit? Inductor circuit. How do I know that's an inductor circuit? Because L is the symbol for inductance. And in capacitor circuits, because C stands for capacitor, current leads voltage. So I'm going to put a little S here and put a little S here. And let's see if that is the case. If we analyze Eli, Eli says ELI, voltage leads current. Voltage is at maximum before current reaches maximum. Take a look at the inductor circuit. And in the inductor circuit that we had a few minutes ago, here's the coil, here's the resistor. What quantity was at maximum at 0 tau? Voltage was at maximum. And then at the end of 5 tau, what current reaches maximum? Current. So that's what allowed us to make the concluding remark, voltage leads current. Voltage leads current in an inductor circuit. That's how we come up with this, Eli. Voltage leads current in an inductor circuit. And then if we go to review, is ice a good mnemonic to describe what happens in capacitor circuits? I for current before E for voltage. So we use this memory tool, current before voltage or current leads voltage. Current is at maximum before voltage reaches maximum. Let's go and analyze what we have for a capacitor circuit. And in a capacitor circuit, R, C, at 0 tau, which one of these quantities is at maximum? The red dot. Current is at maximum before the green dot for voltage reaches maximum at the end of 5 tau. So our concluding statement here, current leads voltage. And is that what we have here? Current leads voltage. Very important memory tool. I haven't shown you the application of this yet. I just want you to digest this as memory tool. I will get into some lessons and some more reference material that'll give you some applicability of this. This leads us into AC circuits and filters. Any questions about this so far? I'll take that as a no. Okay, now let's talk about filters, because all of this will lead us into understanding how filters work. What is the purpose of a filter? Well, let's go ahead and share screen, and let's take a look at filters. Let me find our textbook. Here's our textbook. So I will go ahead and hello, here we are, and here we are. Okay, can everybody see my textbook? Give me a shout out turn on your camera so I can see your smiley
Yeah,
faces.
I can see it.
Cool. All right, so in our textbook, I would like for us to go to chapter 26. And chapter 26 puts us at, I think, my mouse, don't fail me now. Let's do 631. Let's see, am I close? Unit 25, almost. Okay. All right, let me go page down. And let me reduce this. Here we go. Cool. Unit 26, filters. What it is that you need to know. Filters is a very important part of our lesson as we get closer to the end of the semester, because it engages AC, which we will be bringing into lessons starting in earnest this week. We talked a little bit about AC. You've seen oscope waveforms. That's a very nice exercise we've done before. But now we're going to actually use the oscope waveforms and do something with them. And a very practical exercise is understanding filters, low-pass filters, high-pass filters, band-pass filters, band rejection filters. Right now, that's just words to you, but if you look at the visuals in your textbook, you'll have a better understanding what's going on. We happen to have an inductor with a diagonal through this. What is any electronic component with a diagonal arrow through it? What does that diagonal arrow infer?
Variable.
It is variable. I can change the value of inductance by turning a knob. If I have that arrow over a capacitor, I can change the value of the capacitor by turning a knob. Okay, you've already found that out with your potentiometers, right? With your potentiometers, you remember that you could turn the little knob with a screwdriver and you can change the value of the resistor. So the schematic symbol for a variable resistor would be a resistor with a diagonal arrow drawn through it. So we use these for tuning. We use this for tuning your radios in your cars as you go from one point A to point B. When we used to drive more, we used our car radios, and you change your radio stations by changing a capacitor or you change an inductor. And fundamentally, what you're doing is you're creating a filter. Now, with respect to, did I jump too far? Let's see. Oops. This one here is like major jumps. 25, so let me just go. Because what I want you to see are the four basic filters, their shapes and their names. This, my friends, is called a low pass filter. Low pass filter. So let me go ahead and close this guy out. 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 And close this guy out. Okay. All right, so as we're looking at this, this is a frequency response chart. So the lower the frequency goes over here, the higher the frequency goes here. So when I'm saying low frequencies, I'm talking about very low frequencies, okay? And when I'm talking about high frequencies, I'm talking about very high frequencies, okay? So low is your deeper bass tones, if you will, and high frequencies are where your little cymbals and bells and triangle and something like that exists. Yes, I have a bell. And so high frequencies exist over here. And so this is a frequency response graph. It shows how the behavior of a certain circuit is demonstrating in this shaded area what frequencies are being passed. Now, what can the human ear hear? Do you remember your audio frequencies? Audio frequencies, if any of you have ever had a hearing test, on the low side is listed as 20 hertz, capital H and lowercase z is the unit for frequency, 20 hertz. And on the high side is about 20 kilohertz, very high. And so we use a very special circuit. An example of that is shown here, a simple coil and a simple resistor, two components. If I arrange my two components in this fashion, the output signal can be demonstrated with this particular graph. What would my input signal be? Well, my input signal could be your, a practical example of this would be the output of the radio section of your car stereo. And then we would use a circuit like this to go to different drivers of your car stereo system. So in your car stereo system, or any home stereo system, if you will, you should remember you have this. So let's go ahead and do something like, I think I can do it this way. So let me very quickly shift to here, and this will better explain things. Okay, so here's an illustration. And you all have some sort of I think you can relate to this. So here is your TV. Okay, and here you have a big tower floor standing boom chukka hi-fi speaker. And this is the front side of your fabulous surround sound system. And behind the fabric, you might have a driver here, you might have a driver here, and then you have the big hunking driver here, or depending upon the type of speaker you have, you might have more hunking drivers on the side. All right. So in a speaker system, whether this be in your car or whether this will be in your home, the little guy here has a name. I'm sorry, the little guy here has a name. This is called a tweeter. And this guy over here is known as your mid-range driver. And these guys here might have a name, and they might be called your woofers. And each one of these comes in different sizes. So guess which frequencies come out of which size drivers. So the little guy, being really small, small diaphragm, small magnets, small coils and everything, this is for your high frequencies. And the mid-range, guess what? This is for your mid frequencies. And guess what your woofers are for? Boom chucking bass. Okay, so this is what you hear booming down the street before you see the car that's 5 blocks away. And you've all heard this. You've all been in the neighborhoods and you've heard some boom, 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 boom. And then a few minutes later, this car comes screeching around the corner, and that booming is even louder because he's got his windows down and his sound system in the car turned way up. So your deep bass tones come from the big drivers. Your mid-range tones, where the voice, your voice, my voice is mid-range, comes from here. And the little cymbals and the little bells come from the high frequencies, come from your tweeter. Well, your amplifier, the inside your television, will be a signal comes out, and you may have something known as an amplifier, and it comes in different shapes, sizes, and forms. We don't care. And the sound here in the television is full range. And the amplifier handles full range. What does that mean? Well, we stated that your audio frequencies that humans can hear was what? Between 20 hertz to 20 kilohertz. That's described as being full range, and that's what's being processed from your television to your amplifier. Now, the system is tasked with sending that information via speaker wires to your speaker. And in the back of your speaker, there happens to be a plus terminal, happens to be a minus terminal, and that's how you connect your words to your speaker. But inside the speaker box happens to be an elaborate, crossover circuit board. And in that crossover circuit board inside here, we will ask that board to separate the full range into these separate ranges so that only high frequencies go here, only mid frequencies go here, and only bass goes to the woofer. We have to separate this, because if we don't, if we shoot full range into that tweeter will not last more than 10 seconds of playing sound. That tweeter will be burnt out, toast, gone, over and done with. The same token, it's useless for us to send high frequencies to the woofer because the woofer is a big, heavy cone, and it's not capable whatsoever of playing anything in the high frequencies like this bell. It's not going to happen. It will never happen out of the bass, out of the woofer. So we need a crossover circuit board that does these things here, that shoots only high frequencies to the tweeter, shoots frequencies to this driver, shoots bass to this driver. Hence, our crossover board will then take us into our discussion of our textbook called filters, right here. So take a look at this illustration. And as you take a look at this illustration, tell me if I use this kind of a filter, never mind the electronic components in here for now, you'll be able to decipher by looking at the circuit in the not too distant future what kind of a filter this is. However, by looking at the graph, can you make a guesstimate as to what kind of filter this would be used for? Are we going to use this for the tweeter? Are we going to use this for the mid-range? Are we going to use this for the woofer? What do you think is going to happen
for the
here,
woofer.
Gabriel? Gabriel, what do you think is going to happen here?
Gonna go to the woofer.
Because we are passing what frequencies here?
The low pass.
Low pass meaning low frequency. So a low pass filter will pass low frequencies, and which driver produces low frequencies? And Andrew said it correctly also. I heard Andrew in the background said, yeah, and Andrew spoke first. It's the woofer. So not only will it pass the low frequencies, what will it do to high frequencies? What word is used here?
Reject.
Rejects. It rejects the high frequencies, interestingly. Okay. It will reject the high frequencies. So it shows low frequencies passed around the dark shaded area. Frequencies that are rejected here happen to be in the high frequency area. This low pass filter is an excellent filter to use for the woofer. So how do we build that? Our input signal will be divided into three paths, and the path that we feed to the woofer will go through a coil first and then a resistor, and then the output signal here would be appropriate to give us this kind of a response. So this is called the low pass filter. Low starts with what letter, my friends?
L.
L. Pass starts with what letter? P. Filter starts with what letter? F. So I would abbreviate this as LPF, low pass filter. Are we good with that?
Yeah.
Next illustration that I want to show you, they have a more advanced one. We'll skip it. This one is also a low pass filter, and this one is achieved by putting a combination of a capacitor, a coil, and a resistor, so having three components. What this achieves is a more distinct drop-off. It's not a gradual drop-off like what we had before, but this, boom, It gives us a nice flat response and a little tiny bump, and boom, it drops off dramatically. So that means it doesn't allow anything in the mid-range and certainly nothing in the highs to go to the woofer at all. And so this would be this is what we call a steeper response, a sharper curve filter by adding an extra component. And they say so here, sharper rejection curve. The next one I want to illustrate to you is something called a what? High pass filter. And look at and analyze this guy for a moment. Look at the blue shaded area. Which one of these has the most shade? Would be high frequencies. So this particular circuit, which is built with a capacitor and a resistor instead of a coil and a resistor, it's a capacitor and a resistor hooked up this way, will give us this frequency response. So this is called a high pass filter, and it will reject what? What will it reject? Low frequencies, and it passes what? High frequencies. Do I use this for the mid-range? Do I use this for the tweeter? Do I use this for the woofer? What do I use this for? Pauline.
You use that for the tweeter?
We would use this for the tweeter. Everybody agree? This is used for the tweeter. And I can build the third component in here and develop an even sharper curve like this. Then we have something called band pass. And band pass, as you read this, permits only a certain range of frequencies to pass while doing what? Rejecting frequencies where? On either side. What this looks like is here. It's kind of a peaky thing. Frequencies below this resonant point, they call this a point of resonance, is rejected. Frequencies here are rejected, but what's passed is the shaded area, and there's a center point to this bell-shaped curve. It's called the bell-shaped curve because it's shaped like a bell. That center point is your resonant frequency, and this is what we will allow to pass. If I change this with some components, I can make this a little wider. Guess what part of the speaker gets this? Is it going to be the tweeter, the mid-range, or the woofer? Everybody?
Mid-range.
Mid-range.
Mid.
I think so. Yeah, that's a good guess. Mid-range. So by looking at these three circuits, guess what? We've got the different circuits that will be able to take your amplifier signal and feed it to your speaker. Then there's one more filter. This one has several names. It's called a band reject, right here, band reject filter. It's also called a what? The nickname is called a notch filter. And a notch filter does this. It takes a very, very interesting part of the frequency range and does what with it? It rejects it. But frequencies below are going to be what? Passed. And frequencies here are going to be passed. We wouldn't use this for a speaker, I'll tell you right now. This is not used for your speaker. But what would be a good application for this kind of filter? Anybody have a guess?
It will be for like for hearing aid.
For what?
The hearing
Oh,
aid.
for hearing aids. For hearing aids?
Yes.
For hearing aids, would we reject a certain range? It's
like the background noise.
That could be, you know, noise rejection, headphones, hearing aids. That could be one application for rejecting frequencies. That's very good. That's really good. How about another idea for rejecting certain frequencies? Very commonly, if any of you know somebody who does karaoke, nobody here does karaoke, but if you happen to know somebody who does karaoke, of course, if anybody here does karaoke, many of you are reluctant to admit that you do karaoke, so that's all right. You can all be closet karaoke people. But if any of you happen to do karaoke and know somebody who does karaoke, we can reject the voices in a certain range and allow most of the music, the bass boom chukka hi-fi and the tweeters, violins, and whatever else is happening on the top end, lead guitars and things to pass. but we can reject most of the voices in this area and be able to fill in the voice with your voice on the microphone. That would be another application. So the noise canceling is one aspect of hearing aids and noise canceling headphones, and the other utilized for taking out certain frequencies. Why are you concerned about this? The most significant thing that you're concerned about is understanding low pass, high pass, band pass, and especially this one here with the narrow versus the wide band pass. This, my friends, is what's used for tuning your radios. Your radio will have a resonant frequency, a point of resonance. That frequency is what your radio will tune to the station that you want to hear. So Cortez, give me a station number of your favorite station. Don't say KKHI. Give me a station frequency number if you remember it. 99.6, 106.1. Call out something, Christian. Whatever you remember.
106.1.
106.1, that's pretty good. So for 106.1, what that means, my friends, for 106.1, it means this. Simply, on the radio spectrum, here to here, somewhere here is 106.1 megahertz. Somewhere here will be 98.6 megahertz. Somewhere here will be 88.5 megahertz. Now, whatever stations you listen to, you can fill in those numbers, but there happens to be your frequency spectrum, and there happens very specific frequencies that your radio tunes to. So we want the filters to be band pass. We want them to be band pass, and we want the resonant frequency to be equal to your station frequency, equals to your station frequency. And the shape of the band pass, we want this guy to be as narrow as possible. Okay, we want it to be as narrow as possible. And you can control how wide or how narrow this is depending upon your circuitry. Why do we want these guys to be as narrow as possible? Because if they were not narrow, if this 98.6, instead of being shaped like this, might it interfere with another radio station right here at 99.7 megahertz? If I'm trying to tune in this radio station at 99.7 megahertz in green, and all of a sudden my circuitry went wonky in my radio, and all of a sudden, instead of being a narrow spike band pass frequency response, I end up with something really wide. If something's really wide, won't it pick up? It'll pick up the one I want, but won't it also pick up interference from a station that's close to it? Yes. Your cell phone works exactly the same way. Your cell phone broadcasts out at a very specific frequency depending upon your carrier, and we want to make sure that the carriers are separated far enough apart they don't interfere with each other. You want to make sure that your radios have circuitry that is designed well enough with these very narrow tuning circuits, not wide tuning circuits, so that when you pick up one station that you want, you don't hear a station near it that will interfere with this. How many people have ever tuned into one radio station and heard interference from another radio station? Andrew has. Anybody else?
I do, when you go back towards the Lake Tracy and stuff.
Yeah.
Yeah. Cortez, have you experienced that? You tune into one radio station, you hear another one bleeding in?
Yeah, when you're like Andrew says, when you're getting from one area out to the next one where the same radio station number might be two different actual stations.
Yes, that's true. And then so same station number, two actual broadcasting. So here we have overlapping signals, but not necessarily anything bad happening with your tuner. So that being said, we covered a lot of ground today. And so in a quick review, we started off with capacitor circuits. We talked about RC time constants. Sorry. We talked about RC time constants, developed all the calculations, developed frequency response graph. We talked about RL time constants, how coils behave, how they build up a charge or magnetic field, and how they allow current to flow, and which one comes first. And then we developed a memory tool, Eli the Iceman, and the most profound thing is to remember voltage leads current in what type of circuit? Inductor. Current leads voltage in what type of circuit? Capacitor circuits. And then we also touched on filters, and the filters being a practical application. Most practical application is dividing the full range sound from your television through your amplifier, and as that full range is fed into the speaker, full range is not delivered to the tweeter, mid-range, nor woofer. We have to use crossover circuit board that has low pass, high pass, band pass filters built into that circuit board in order to shunt. What frequencies to the tweeter? High frequencies. What frequencies to the mid-range driver? Mid frequencies. And what frequencies to the woofers? Low bass frequencies. And so, and then the practical application, another practical application of filters in broadcasting and radio stations is band pass for specific selection of radio stations. And we do not want a wide band pass. We want very narrow band pass filters for that application. So that, in summary, is our lecture for today. I would like to stay behind for any questions anybody has regarding the superposition exercise. Let me take a quick peek at superposition. Grab the wrong mouse. Let's grab the mouse here and see. Rolando has submitted this, and take a quick peek here. Rolando has submitted, so has Christian. And as I look at Rolando's, we have our final. Our final is good, good, and good. And that direction, those are correct. Excellent there, Rolando. So you have a score. Let me take a look at Christian's. At Christian's, let's take a look. You have that direction, and those values. That looks good. And you also have an excellent score there. And then we jump to the next entry. Gabriel, you haven't done this one yet. So Andrew, let's take a look at yours. Here. No, we want to hang on this. Your directions of current are correct. Your values of current in the final analysis are not correct. In fact, your analysis of current is, no, your R values. So we're gonna have to talk about this. So we're gonna need some work with that. And if Kyle is submitting the same paper, yeah, you guys, you really need to do your own work because I'm looking at values that are the same. So it looks like, you know, one person's doing this, and you're making the same same conclusions, which is,
we sit down and work on it together and help each other through it all.
well,
so,
yeah. Yeah, well, you're heading in a direction that has me concerned. So I will want to review that with you.
Okay.
So stick around, both of you. Pauline, solid. Your analysis is solid. Let's take a look at your voltages at the end. That looks great. And then Okay, so everybody who has submitted a superposition exercise, so Mr. Cortez and Mr. Bolito and Pauline, you submitted, so your papers are good. And I will have a follow-up superposition exercise just to give you more practice on this. And for our friends that were not part of last week's discussion and also did not submit something, that would be Kyle, I'd like for you to hang, Andrew, and Rebecca, I'd really like for you to hang if you could, and Gabriel. So if the four of you can hang, and Wenbin, very important that you hang also, because I did not see a submission from you for a superposition. And you don't want to fall behind on this because it's not hard, but it is a fair amount of work in order to resolve a solution, okay? Okay, and then as far as timers go, I can see 555 timers for Gabe, Andrew, Kyle, Sheehan. I'll review those and make sure that they're all blinking, and that'll be good. So for Rolando, Christian, and Pauline, do you have any remaining questions for me before I let you go?
Yeah, I have one on the reading cap value.
Yes, reading the capacitor values. Yes, what about?
How do you get the 320? The answer was 320 nanofarads. So from the number, the cups number was
okay,
324.
let's take a look. It's okay, yeah, no, let's take a look. Yeah, 324.
Number of the cup.
Did we do things?
Yeah, 425.
Well, we had a 324 in this particular one. Was this
that one?
This one here?
How do you get the value ending 320 nanofarad?
320,
After reading.
4 zeros. Let's take a look. So 32 with 4 zeros. Is that how we interpret it?
Yes.
Okay. And so this is picofarads. We moved the decimal point 3 places over. And so that will become 320 nanofarads. If you key this into your calculator and let your calculator do the conversion for you, you will also have 320 nanofarads.
I got 3.2 microfarad. I don't know how to get 320 nano. Can you show me your calculator how you proceed the operation?
Sure. Let's try this. 3, 2, 1, 2, 3, 4. Okay. Second exponent negative 12. So the keying in there and hit enter. Isn't that 320 nano?
Put 320 exponent 3. Exponent 3.
There's nothing exponent 3 in this particular case.
Oh, how do you put 3? So you just say 320,000?
I just typed this in exactly as we wrote it. 3, 2, and 4 zeros.
Why not 320 exponent 3 first?
Why should I do 320 exponent 3 when I got an exponent negative 12 at the end?
Oh, I did 320 exponent 3 times.
No. Yeah, don't do it. Yeah, don't put in two engineerings. don't put in a kilo here and then put in a pico there. Just do this as a straight decimal number. 320,000 exponent negative 12.
Okay.
Yeah, you're putting in two engineering prefixes in one exercise, and that we don't do that.
Oh yeah, I got it.
Hey, Rolando, are we good with this now?
Yeah, finally I got it.
Okay, I'm glad. Yeah, so if there's any, that's great. Yes, I can see that on your screen. That's wonderful. So if there's any follow-up questions like that, now's the time to ask. So Christian and Pauline, did you have any follow-up questions as well?
No, I think I'm good. Thank you so much.
Okay, you're very welcome.
Yeah,
and Christian, you're okay. All right. So Before we dismiss you, let me go ahead and take a screen picture with all your smiling faces for the dean. So if you can go ahead, put on your smiling faces. And let's see, how do I do this? Oh, I know. Let's go here and let's go here. Move the camera out of the way for a moment. There's my smiling face. Yes. Okay, 1, 2, and smile. Jeez. Okay, got your smiling faces. Great. Dean is happy. So we will dismiss Mr. Cortez, Mr. Bolito, and Ms. Sheehan for now, and the rest of you hang on with me. And I would like to spend a little bit of time with you on the superposition thing, okay? Okay. Have a lovely week. Keep an eye out for Canvas. There's going to be a lot of stuff coming your way. Guaranteed. Take care. Okay, so for Andrew, Kyle, Rebecca, Wenbin, and Gabriel, the thing about superposition is, first of all, per my reading, let's go here. Let me go ahead and let me see if I can do this particular one. Take this one, go here, and then grab this guy and pull it up. Can I grab this guy? Okay, I can close the book. All right. So, all right. YouTube. So in YouTube, FRANK space KO space would help. Tap my friendly face. Tap videos. Okay, everybody looking at my YouTube screen? So in the YouTube screen, I prescribed a very specific sequence for you to view things that will be helpful in working out superposition theorem. So superposition theorem is not hard, but it does engage a number of steps. So first thing I recommended was series aiding and series opposing video. This was our lecture from last week. And if I just find a handy screen or do this, I have it here. And I have it here. Okay, I'll pull it out. Just review better than... The YouTube video goes to give you the verbalization behind our discussion. I will go ahead and verbalize our actual note page from last week. And that's this guy right here. Let me position this so we can see this better. Okay, so series voltage sources. So that video, which is about 20 minutes long, works out an explanation about series voltage sources being either series aiding or series opposing. Fundamental concept that you need to have a grasp of before we progress. And this is fundamentally what you have in your flashlights. In a multi-cell flashlight, or what you also have in your battery pack, your battery pack, this guy here, is set up as series aiding. There's wires that crisscross back in here in a zigzag pattern. Then when I pop in that third battery down, I will be able to have a total of 1.5 plus 1.5 plus 1.5, giving me a total of 4.5 volts on these two wire terminals. That's called series aiding. It's called aiding when the sources move current in the what? Same direction. That's what we have here. This is moving electricity to the left. This one moves the electrons to the left. This one moves the electrons to the left. They're aiding, and they're working very nicely. So this one wants to move electrons to the left, left, and left. Here, if I take one of these batteries, like our battery pack, and instead of putting it negative and positive, if I reverse this guy, oh Lord, that's not good. What's going to happen is I'm going to kill my batteries. And I have one source moving to the left, one moving to the left, but I've got one wire backwards moving electrons to the right. This I have series opposing. So that's where the voltage sources are not moving everything in unison. There's kind of opposite currents going on. So if each one of these guys happens to be 11 volts, what is my total? Well, the way we reconcile this is with a simple left-right arrow chart. Currents moving to the left, I draw an arrow to the left. Currents moving to the right, I draw an arrow to the right. I have two that move to the left, so I write 11 volts and 11 volts. I only have one that moves to the right, and I have 11 volts here. Well, what happens is these 11 volts cancel, leaving me with a net of 11. But what column is this 11 in? It's in the left-bound column. So that tells me my final current, these three combined, will result in one circuit that looks like this. The final current moves the electrons to the left, and the final value for voltage is calculated as 11. If I show you another example here, and this is in the video, so this wants to move to the left, to the right, to the left, to the right. I do a left-right arrow chart, I write the values in, and then I discover the majority of voltage is moving current to from the source, moving it to the left. So my final circuit with one voltage source shows the negative plate moving electrons to the left, comes down, goes this way, comes back up, back to the source, okay? So, but what's the difference? The difference is the larger subtract the smaller. So my net voltage, my VS total, works out to be 4 volts. What is my current in this case? Well, if I have a 2.2 k ohm resistor, I calculate this current. What is my final direction going through the resistor? Well, the electrons from the source move to the left, then down, but through the resistor, they move to the right, as shown by this arrow right over here, okay? And then back up to the positive plate of the source. So that, in summary, is understanding series voltage sources. They could be either aiding or opposing, but that's only if they're in series. The next thing I talked about was Kirchhoff's laws. And in Kirchhoff's laws, what we had talked about, and there's a separate video on this. So the first one for series aiding and series opposing, that was about 28 minutes. And then if I go to here, go to here, you will see there's a series aiding, series opposing, and then over here I have Kirchhoff's voltage and Kirchhoff's voltage law, Kirchhoff's current law. So if I click on this guy's a 45-minute video explaining the piece of paper that's in front of me now. And you should go through that video a couple times in order to fully appreciate it. But in a nutshell, what it is that we have, Kirchhoff's laws, there's two of them. There's a Kirchhoff's current law, which we abbreviate KCL. There's a Kirchhoff's voltage law, which we abbreviate KVL. Current law states the sum of all currents entering any node must equal the sum of currents exiting that node. Look at that in that video, write it down in your notebooks. That's an absolute. KCL is defined this way. Let me give you an illustration how to understand that. Here I have a node. Wires attached to the node. I have currents going in, currents coming out. How do I reconcile what's happening on this leftover wire? I reconcile what's happening on this leftover wire by creating an in and out chart. The in and out chart goes to show my inbound currents, I write the values down. My outbound currents, I write the values down. This totals 27 amps, this totals 14. Well, according to Kirchhoff, and this is a law, this is not a guess, this is not a hypothesis, this is a law. One side has to equal the other side, according to Kirchhoff. Somehow there's an imbalance. We know ultimately 27 has to equal 27. So there's a missing current. What is missing is simply subtracted. 27 take away 14 gives you 13. So the missing current is 13 amps in which column? The outbound column. So you can decipher that remaining wire is 13 amps and the direction is out based on these numbers. I'll give you another example. Here's another node and here's a bunch of wires showing in and outs. So I do the same thing, do an in and an out, write down all my in values, write down all my out values, tally them up. Is there a difference? Yes, there is. Which one's bigger? This one's bigger. So my final direction of current is based on where the bigger number is, and it happens to be in. And so this one happens to be, the bigger number is going to subtract the smaller number, and the difference is going to be my missing current. So 6 amps is missing on this side in order to total 39, yes? So 39 must equal 39 according to Mr. Kirchhoff. The missing current has to be 6 amps, and what column is it in? It's in the outbound current. So 6 amps, arrow going out. That's Kirchhoff's current law. Now, all of this is based on us using electron flow model. An electron flow model means current leaves the negative side of the voltage source through the circuit and returns to the positive side. Also, current flows from the negative side of a device through them to the positive side of those devices. Using that, we'll go into the next sheet in a moment. We talk about Kirchhoff's voltage law, KVL, and this is the best definition for KVL. There's several, but I chose this one, number one. And what this says is the algebraic sum of all voltages in any closed loop must add to 0 volts. Look at this first loop, and I'm going to start at point A, and I'm going to go around the loop until I come back to point A. I'm only going to do this little square here. So where does this circuit come from? This circuit came from the previous week's lesson, and the previous week's lesson was a 5 resistor series parallel circuit that we had done. And that 5 resistor series parallel circuit that we had done was this guy here on the previous week. Series parallel analysis, 5R, because 1, 2, 3, 4, 5. We've done all of this. We did the analysis, we did the currents, we did the totals. We got values. So we're using this as a model for Mr. Kirchhoff right here. This circuit is this circuit. And so what did we do here? What we did was our final analysis gave us very specific values for voltages and polarities. So these were the polarities that were determined, and these are the voltages that were determined. So if I start at point A and I go around in a circle, the very first thing I encounter is a negative 8.94. I write down loop 1 is a negative 8.94. Now I'm on this side of the resistor. Now I want to go down. As I come down, I see a negative 4.38. So I write down negative 4.38. Now I'm on this side. So between here and point B, there's nothing. There's no wire. But between point B going back to point A, I encounter a positive how much? 13.32. So I add a positive 13.32. So if I add these 3 voltages in this, what type of loop? Closed loop. Algebraically, they must add to 0. Do these algebraically add to 0? Yes. Is Mr. Kirchhoff happy? Mr. Kirchhoff is very happy. But that's only one loop. Let's take a look at another loop. Here's another loop. And in this loop, we start at point A, go down, go over, come up, and back to point A. The first thing we encounter is a negative 13.32. Then we encounter a negative 10.28. Then we encounter positive 28. Then we encounter a negative 4.4. Write those down, add them up, we get 0. Is Mr. Kirchhoff happy with this loop? Hallelujah. Then there's a big loop. We start at point A and we go from here up to here, up to here, 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 here. So this outside loop, we actually have 3 loops here. So if our analysis was correct, everything should add up to 0. And guess what? When we go around that loop, it adds up to 0. So this is a quick synopsis of what's happening with Kirchhoff's voltage law and Kirchhoff's current laws. Based on this, then and only then, do we enter the realm of superposition. And when we enter the realm of superposition, we have this guy right here. And in this guy, superposition is used for analyzing where you have multiple voltage sources but they're not easily reconciled for series aiding nor series opposing. Here I have a VS1, here I have a VS2. They're not in series, they're on opposite sides of the circuit. So I can't take big one, subtract small one. It doesn't work that way. But there is a method, and the method has 4 steps. And the 4 steps are noted here, 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 and here. And in the YouTube, that this particular lecture, which you need to review, if you haven't, and review it again, is a little over an hour. Fundamentally, if you follow the steps, it says replace voltage source 1 with a wire and solve. Well, I take voltage source 1, I redraw this circuit here, I've replaced voltage source 1 with a wire shown in green, and then I solve. And we can do this. This is only 3 resistors in parallel, series parallel. When we go to do this, I have a redraw and I have another redraw that gives me a total current. I take that total current, bring it up here, and I discover that 200 milliamps flows through R3. Then it goes to node A. That 200 milliamps flows through R3 into node A, then it splits. Since these ohms are equal to these ohms, I can use current divider formula and find out these currents. I find out that information, I enter it into the first table for step 1. So step 1 was here, step 1's results are here. It's not important we calculate voltages now. What is important is we reconcile our currents. And so we reconcile that the current for R3 was to the left. Here's R3, it goes to the left. It was 200 milliamps, it's 200 milliamps. The current through R2 is down of 100 milliamps. So here's the arrow down, 100 milliamps. The current through R1 is to the left of 100 milliamps. Here's left, 100 milliamps. That's all we need to solve. We can calculate the voltages, but we don't need to do that. That's all we need for step number 1. You want to repeat the process, but following step 2. Step 2 says now replace VS2 with a wire, bring back VS1, and solve for all of this again. And so when we follow that, we have this redraw. I replace VS2 with a wire, I bring back VS1, and I solve for series parallel, do my redraw, have an RT, calculate total current, bring this information back up, use current divider formula to find out these little currents. The bottom line is, in this particular analysis, based on electron current flow, I can see the direction of current through R1, R2, and R3. R1 and 3 are still to the left, but R2, interestingly, instead of going down, is going up. So I fill that in my second chart for step 2. Resistor number 1 and 3 are flowing to the left. Resistor number 2 is going up, and these are the values. So I've completed step 1, completed step 2. In step 3, it says algebraically add all currents through resistors based on current paths. Now, previously it said something else, but I whited it out and I wrote down currents through resistors. And how do I algebraically add? Well, check this out. R1 moves to the left, 100 milliamps. R1 moves to the left, 312.5. They're both moving in the same direction. I add these two to become 412.5 milliamps. Take a look at R2. Current goes down of 100 milliamps. Current goes up of 187. They're going in different directions. I cannot add. The bigger one must take away the smaller one. 187 take away 100 leaves me with 87. Which one was bigger? The current going up. So my final direction for current is going up. My last one is to look at R3. R3 goes to the left, R3 goes to the left. 200 milliamps plus 125 gives me 325 going to the left. So when I algebraically add, I'm algebraically adding the currents based on the direction of current flow. I end up with total current. Once I have the currents, I can finally calculate the final voltages using Ohm's law, because the ohms don't change. R1 is still 20, so 20 times this current will give me this voltage. 20 times this current will give me this voltage. 30 ohms times this current will give me this voltage. So right now, these are my concluding numbers based on this part of our analysis. I'm going to do a final draw of my original circuit. I'm going to expand this and make this guy bigger, but I'm going to use this information here. So using this information here, here's my big drawing. And my big drawing shows this circuit magnified, my voltage source 1, voltage source 2, R1, R2, R3. I said R1 was 8.25 volts, moving current to the left, 8.25 moving current to the left. So from my previous definition of electron current flow, this side of the resistor must be negative, this side must be positive. Take a look at my R2. R2 is the final current going up of 87.5, giving me 1.75 volts. In my big redraw, I show an arrow going up, so it must start at the negative side of the resistor, go through the resistor, going to the positive side. And my voltage is 1.75. Then the last part here, current going to the left of R3 of 325 milliamps of 9.75 volts. Current to the left, 3.25 milliamps, 9.75 volts. So all of the information here, these arrows, these currents, these voltages have been transferred back to an enlarged drawing of my original circuit right here. And I've had to mark in the polarities based on my definition of electron current flow. And my definition of electron current flow was current flows from the negative side of a device through them to the positive side of the device. So as the current flows through R3, it must flow from, in this case, from the right to the left. This right side has to be negative. This other side has to be positive. As the current flows from the bottom through the resistor to the top of R2, the bottom must start at negative, through the resistor, end up on positive. That's how I confirm my polarity there. The current that we determined for R1 was left. So as it flows from the right to the left, this side must be negative. This side must be positive. So the polarities are based on the direction of current flows that you determined in step number 3. Now, what was step number 4? Step number 4 says check results using what? KVL. What was KVL? KVL was adding voltages in a, and algebraically we said all the voltages in a loop have to add to 0 if our polarities and numbers were correct. So let's go ahead and see if that is true. So when we go to check that, guess what? I've labeled these other points. This is W, A, I had an A and a B, so I labeled this W, X, Y, and Z. So I'm going to create a loop. And the loop direction will start at A, go to point B, go to point X, go to point W, and then end up at A. So my loop is going in a clockwise direction on the left-hand loop. So if I start at point A and come down, the first polarity I encounter is what? Positive, what value? 1.75. So I write down plus 1.75. From point B to point X, so here, point B to point X is my next travel. There's a nothing on a bare piece of wire. From point X to W, because that's my next route of travel, X to W, I encounter what polarity first? Negative what amount? 10. So I'm going to add plus negative 10. Now I'm at point W. So from point W, I have to end up back at point A. So here's W, here's physically A. As I bring point W, bring my probe over here, what polarity do I encounter first? Positive. What value? 8.75. So I'm going to add a positive 8.75. When I do the math, my first loop tallies what? 0 volts. Is Kirchhoff happy with my first loop? Yes. Take a look at my second loop, A, Z, Y, B, A. So here's A, here's Z, here's Y, here's B, back to A. So here, again, I'm going in a clockwise direction. It doesn't matter which direction I go, as long as I start at a point and end up at that point. I'm starting at a point, and the first thing I encounter moving clockwise is positive 9.75. So I add 9.75. The next thing I encounter when I come down is a negative 8 volts. So I write down add negative 8 volts. Nothing on this piece of wire. And then I encounter a negative 1.75 volts before I get to A. So I add negative 1.75, and guess what? If I go to add, I come up with a 0. Is Mr. Kirchhoff happy with the second loop as well as he was with the first loop? The answer is yes. So that means our polarities are looking pretty good. But we have one more loop to do. We have a big loop. And the big loop, WAZYBXW. So WAZYBXW. So by writing down the letters here, it tells me my travel starting at point W and going all the way around. And when I go to do that, I write those values down, end up with 0. Is Mr. Kirchhoff happy? And that is a yes. When these add up to 0, then that proves to you that your analysis here is correct. All right. And so if Kyle and Andrew can pull out their paper, and I'll show you fundamentally the first area of concern, and some of you might benefit from this right here. Okay, so let me do it this way so we can all benefit from this. I will go here and here. We are day 50 day. So Andrew and Kyle, do you mind me putting up your analysis on the screen for our friends to share? Is that okay with you guys? I can't hear you.
Yes, that's fine.
Okay. All right, so let me get it here. 50 day, go to
No,
here.
I am.
And then go to here. It's taking a moment. Can't blame this on YouTube. All right. And let's go in this direction. Go in this direction. And let me find it. I think it was. Okay, here we are. Superposition. And let me open it up. So we won't go through the whole thing, but I think if I go through part of it, it'll help you understand what's going on. All right. So widen this here and add plus here. Okay, that's pretty big. All right, let me share the screen here and here. Okay, so as we go to analyze this, here is where I want to point things out to you. Papers away. All right, so the first step of our process was to replace voltage source number 2 on the left side with a bare wire. Did I draw this with a bare wire? Up here in this corner here, yes? There's no more voltage 2 in this redraw.
Yes.
So I did the first redraw for everybody. And then you analyze the circuit based on what you see. So if you analyze this circuit based on what you see, first and foremost, your values of R are not right. The values of R come directly off your circuit. R1, 4.7 k ohms goes in this cell. R2, 6.8 K ohms goes here, 10 K ohms goes here. So immediately you didn't fill in the numbers for your resistors as they were originally given. I don't know why you changed those. There was no reason to change those. The R values
For some reason, we figured I'd take voltage and the V and I and then times those to get R.
No, because you don't have an I. You don't have an I until you get R, until you get to an R total. So in following the steps, of our analysis, the R values are simply as they are given. Okay, so they're given. There's nothing to do there other than accept the quantity that is given. And let me get a piece of paper here. And so in the first part of our analysis, you have this guy here, to here, here.
Get this out so that I could just fill it in real quick.
Okay, so R2, R3, R1, and 5 volts. Okay, so I will go off of the screen for a moment and go back to my camera. And so I've just done a quick redraw of this circuit. And in a quick redraw of this circuit, I have a 4.7K, I have a 10K, and I have a 6.8K. I put my eyeball here, as we've done, and look back at the circuit, and I see that there's a relationship between R2 and 3. Rebecca, what relationship, if you put your eyeball here and you look back at the circuit, because the voltage source is this guy, we put our eyeball on the far side of the circuit here. What relationship, Rebecca, do you see as a relationship between R2 and R3?
They're in series.
Do they share the same current path, or are they in different current paths?
They share the same current path?
Well, let's take a look. And that's an important observation. Are these two connected at the same node? And let's call that A.
Oh, they're parallel.
And then the other side of these, and I'll go ahead and do this. The other side is, let's use blue. So the other side's connected to a different common node called B.
Yeah, they're parallel.
So they're not in the same current path, because if you take a look at the electrons will leave the negative side of the source, come down here, go here, and what happens at node B? They split. So part of the current goes that way, part of the current goes this way. So that tells you that the current path of R3 is different from the current path of R2, because R2 comes back around this way, R3 comes up, and when these two currents come back to node A, they combine to come back to the source. So this is how current flows. Current will leave the negative side of the source, come to B, split apart. So 2 and 3 are not in series, they don't have the same current path. And if we follow the definition for parallel, that means they are in parallel with each other. So we can redraw this as an REQ showing R2 parallel with R3. Question?
Oh, I was going to give you the answer of what that turns out to.
Cool.
That I got.
What do you got?
4.05.
Yeah, 4.05 kilo ohms, yes?
Yes.
And you have 4.7 kilo ohms over here. So this will give you the final circuit. The final circuit looks like this. You'll have an R total. Sorry, you'll have an R total that is equal to REQ1 plus 4.7. So this will be 8.75 K ohms, yes?
Yes.
Right? Okay. So in your chart, my friends, you have an R column, you have an I column, and then you have a direction column, direction of current. So the R value, and we only need 3 here, R1, and R3. The R value was 4.7K. This guy is 6.8K. This guy's 10K. And so as we analyze this, which direction does current flow through R1? Left, right, top, or up or down?
Left.
Okay, it flows to the left. Andrew, how about the current that flows through R2?
To the left also.
Okay, to the left. And how about the current through R3?
It goes up.
It goes up. Rebecca and Wenbin, are you okay with this?
Yeah.
Okay. Now you have to determine the amount of currents. So the amount of currents is going to be determined as 5 volts over 8.75 k ohms. So what is my amount of current here? Take 5 divided by 8.75 k.
I came up with 571.4. What is it called?
What's it called? Come on now.
I'm working on it. Micro ohms.
Current. Microamps.
Microamps.
Okay. Okay. So you will end up with, what did happen here? So we have 8.75. So 5 divided by 8.75. So you end up with 571.40 what?
Microamps.
43.43 microamps. Goes down, up, and this way, yes? We take that information from this circuit to this circuit. Here, here, up, and over. Wow.
Peppers too.
You have just found the direction of current through R1. It's going to the right. And you also found the value of current through R1. Because in this schematic, the value through R1 works out to be 571 point, let me look here, 43 microamps. Is everybody okay with that? Now,
yeah.
So you have 571.43 microamps leaving here, coming up, and going back. Now, you also have 571.43 microamps coming into node B before it's split up between these two guys. So you use current divider formula to find out how much current is split between these two guys. So current divider formula, if you recall, your IRX is equal to RT over RX times I total. So if I want IR3, what am I going to use for R total? Am I going to use the 8.75 R total for the entire circuit? Yes or no?
No.
What should I be using, Andrew? What do I use for RT for current divider?
I'm looking at my thing.
REQ?
REQ here. We're going to use this REQ because these two guys were reconciled to be parallel. They came up to a total, and EQ is the total of the two in parallel, of 4.05. So I'm going to use 4.05K here, and then the value of 10K here, and I'm going to multiply it by my 571 microamps. And when I do this, I'll get a current that goes through R3. So can you do that? 4.05 divided by 10. You can leave out the K's because they cancel. So 4.05 divided by 10 times 571.43. And what do you get?
405.
You're going to take the 4.05, divide by 10, and multiply by the 571.43 microamps.
231.43.
What do you get? 400 what?
231.43.
231.43 what? Apples? Oranges?
Milliamps.
Microamps.
Micro.
Okay. And then if you do the current divider for the R2 value, so IR2, your IR2 is going to be equal to 4.05K on top, divide by 6.8K on the bottom. The K's cancel, so just do straight numbers, 4.05 divide by 6.8 and multiply by the 571.43 microamps. What do you get for IR2? Rebecca, do you have a number yet?
Sorry, I didn't hear you.
We're calculating IR2. And we're calculating the current through R2 using current divider formula because the 571.43 comes into B, it's split. We've already determined the amount that splits up through R3 was 231.43. We now need to determine the amount of current that splits up through R2. So we use current divider. We use the total of the bank, which we determined earlier as this number based on these two guys being in parallel, giving us this as a total. So we use REQ as the total, 4.05. The denominator is going to be the value of R2 right here. So 4.05 divided by 6.8 times our total current coming in of 571.43 microamps.
Okay, yeah, I have the total.
Sure, what do you got?
It's 340.34 microamps.
Excellent, okay. So something, you know, we should be within a few hundreds with each other, okay? So this is all you need to do to analyze for step one. Step one of the entire superposition process. Step one of the entire superposition process is to simply fill in the chart for currents and directions. It's right here, okay? All we want to achieve for step one is final directions and currents for our first redraw. Step two asks us to replace one voltage source with a wire and bring back the other one and solve for this again. So in your worksheet, I've given you, in your worksheet, in the second redraw, I started the second redraw for you. We took VS2, brought it back in. VS1 has been replaced with a wire, and now we solve for the circuit from this corner because the voltage source is here. And as we look at it from this corner, what is the relationship between R1 and R3, Kyle? What is the relationship between R1 and R3? Because they're closest to your eyeball. Can't hear you, Kyle.
Parallel?
They're in parallel. So you would have a parallel R1 and R3 giving you 3.20 K ohms. And then when you reconcile that with your final resistor here, it gives you a total of something very close to 10 K ohms. Based on that, you will do a complete current analysis like what we've done here. So you're just going to go through these steps, but with your new circuit, bringing you down to a total resistance, calculating a total current, taking that current back up, and then building your second chart. And based on building your second chart, then the last step of the entire process is to algebraically add these values to get to your third chart. So you look at the currents for R1, in this case, in our example lecture circuit, they were both moving in the same direction. If they move in the same direction, you sum 100 plus 312 gives you 412.5. In this case of R2, this one current going down, this one current coming up, they're antagonistic. The bigger current going down, current coming up, they're antagonistic. So the bigger one, 187.5, will subtract the 100, leaving you with a net of 87.5 final current going up. And then the last current for R3, this goes to the left, this goes to the left. So you simply add 200 plus the 125, giving you 325. Once you have these final currents, you can determine these final voltages. So Kyle and Andrew, does this help you redo your paper with a
Yes, it does.
better understanding what has to go where?
Well, we see what we messed up on and stuff now. So thank you very much for running through and helping us with that.
Yeah, you're very welcome. And Rebecca, does this kind of help you with this added verbalization so that you can get started on these exercises?
Yeah.
Okay, all right. So if any questions happen along the way, be sure to engage me through Canvas. And
Would you like Kyle and I to redo it and give you the new numbers that we come up with?
Yeah, you're going to need to redo it. Otherwise, the score is going to be less than what you're going to be happy with. Okay.
Okay.
So yes, you are allowed that redo. So if you could do that and get that posted in there, you'll see the updated grade the next time we meet. Okay.
Okay. Thank you.
Okay, my friends, are there any remaining questions that any of you have? Okay, I appreciate you guys making the added time for this. I
had
know
a
this is a whole lot of extra time, but I don't mind doing this. I'm happy to have invested this time for all of us to get a better understanding of some very important topics. So who had a question?
Gabriel.
Gabriel, yeah.
So I know, so I got to print out the superposition analysis, and I did get to do it. I somehow, as far as me turning it in, I usually do it on my phone, and the app was having some defects. So when I went back to the modules to go try to click on the link for the superposition analysis, it kept telling me access denied. So I could, so basically what I was trying to do was download it onto my computer so I could rewrite it for you and log it into the modules. But since I couldn't get it to download back on my computer, I couldn't submit it. So is there a way you could send me the download? That way I could redo it on the computer and just send it to you, submit it onto Canvas instead of sending it to you through the app on my phone?
Okay, first and foremost, you shouldn't be using your phone for anything having to do with Canvas other than looking, okay? You should not be doing submissions on your phone because it doesn't have the power to do things the way that you want. So all of your submissions should always be through a regular computer, first and foremost. To answer your question, can you get a blank copy of this? A blank copy of this is in your Canvas email. A blank copy of this is also in week 12 of Canvas. So you can get a blank copy in two places, either through your email, which you can open up on your computer, or you can go straight to Canvas week 12. You'll see the assignment in week 12. You'll see a blank version of it.
Working for me,
and
so I'm
download it.
Try the email.
Okay, so whichever works for you to print out a copy or to work on it, you have two different ways of doing that using your computer. Okay.
Okay, thank you.
Okay, any other questions, my friends? Okay, if not, then I wish you all a lovely evening. Keep an eye out for Canvas for other things coming your way, and other things will be coming your way. And have a safe week until we meet again next week. So take care. Bye-bye now.